Okay. So welcome for the second day of our workshop. Today is going to be all discussions. If people are joining them on Zoom and YouTube that have something to contribute to discussion, please do. And we now have to choose our first topic. First topic. And why do I have audio feed? Why do I have audio feed? Are you muted?
This is unmuted, but it's supposed to.
Unmuted, but it's supposed to. Yes. Okay, so there is some feedback from somebody. And now we have.
This could be from me.
Okay.
Yeah, that was from me. I have to close my browser and reboot because I have an update from the computer, but it's just a couple of minutes.
The audio shouldn't go out of the hour. Oh, let's see. Yes, so this is question. Okay, so I don't know why. I thought I checked it before. Okay. Oh, wait, technical. Okay, we unfortunately don't have the list of topic somewhere because it would have been nice to. Oh, you have it there, right?
I'll share mine.
You don't need to share. Oh, yeah, you need to share.
I'll share it. The rest people can see it on Zoom. This is what we had at the end of yesterday. In no particular order.
We should wait for Marcel to
come back because yeah, he needs to be. We need any discussion that involves him. He'll only be here in the morning. But maybe Susanna has comments already. She's also only going to be here in our morning.
Maybe we can start putting the stars on or upvotes around. So let's see. For the morning, for me, let's put an asterisk next to the. So I would vote for field theories and the integral. Yeah, those are the two things that I think would be better.
Make sure to have Marcel and Susanna for.
Yes. So I don't know if you guys have preferences.
For the morning?
Yeah.
Me too, those two.
Susanna, you have preferences?
Not really. My topic is there with the start, so I'm fine.
Okay.
Should we start? Because the problem is that with update, we never know how long it's gonna be because it can be like 30 seconds or it could be 15 minutes. Then we have no way of knowing.
Sure. Should we start with defining an integral corresponding to the fraction capacity?
Yes. So let's start with that. And so I write on the tablet. That's probably the best thing. So check the tablet. Okay, so put webinar on the side. What do I need to tell you? It's really bad.
I mean, there's the same task I had at IPMU. So if you want, the slides are helpful, but I don't know. For motivation, maybe the analogy, but like how it works in the classical case. We want to understand are these structures specific to classical or quantum?
Okay, so okay, let's do that. Let's say that we have a measurable space with our omega and sigma omega, and then we have a probability measure from a sigma omega to 0, 1, because it's a probability measure. And then we have an F that takes elements of the sample space and goes to R. And then we can define the, let's put an L here. This is the Lebesgue integral from with F d. And this is the expectation of F. Okay. Now, what we have instead is our ensemble space. Then we have X, that is the extreme points of the ensemble space. Then we have an element E inside the ensemble space. And we can define a fraction capacity that essentially takes the sigma algebra of E in general and gives us a number from 0 to 1. And then we can, in principle, the fraction capacity, this is the F cap lower E. We can restrict it on X. And now we have the sigma algebra over X, so on the extreme points, to 0 to 1. And then we have a linear functional F that takes an element of the ensemble space. And feel free to stop me whenever it's unclear. I'm just trying to get everything out of my head. That goes to R, and we know that this is affine, so we know that F P A plus P bar B gives me P F of A plus P bar of F B.
And this is now with real numbers, or is it still with your convex operation?
These are real, but the A's and B's are not the fraction capacity, not the measures themselves.
So this is the convex operation, but this is the linear operation of R.
On the field, on the real numbers.
Yes.
Well, if you want on the interval 0, 1. But it will
Well,
definitely in R.
F isn't not is F on the interval 0, 1?
No,
Oh, sorry.
Yeah.
Sorry.
this is on all the way.
Yeah, absolutely.
Right. In fact, this is an affine function, so you can define it like if you imagine E embedding in a vector space.
Yeah.
Then you can fix an element as the origin, and then it's an affine functional. So you can say the F is of E is going to be F at the origin plus a linear function.
And by affine, you mean that it preserves convex combinations in that sense. That's what your
Yes,
definition of
but-
affine is. Because
So affine, everything that preserves a convex combination is an affine function, meaning affine on a vector space. It's an affine functional is a linear functional plus a translation. Right. So if you had, let's say you had Rn, right, and we have, let's say, a G on Rn to Rn, or
Okay,
another
I see.
vector space.
Yeah. Okay.
It's affine if it's basically if it's linear plus. And that actually is something that is not, it's simple to prove. But yeah, preserving convex combination means that you're affine. Okay, so we have this and it's defined on all of E. So now we can, of course, define f restricted to x. So now this is going to be a function from x to r. And so what we're basically looking for is for some type of integral of the ensemble space that take the f restricted to x and the fraction capacity and gives us back f at the point over all of B.
So not just any extreme point, but any point, right?
For any point, yes.
Because you have the values on extreme point.
Right. So the fraction capacity will restrict, actually, this we can say restricted in x as well. So Marcel is back. Good.
Yeah, he was there.
This is because essentially the convex combinations are typically sigma additive extreme points, linear combinations of the extreme points, right, by the Choquet theorem. But this makes you suspect that you can do this, right?
Say it again.
So this f is affine, right?
The f is affine, yes. Big F is affine.
Yeah. So the idea is that since the extreme point since you're having an integral over extreme points,
Yes.
and the idea of Choquet's integral Choquet's theorem is that you can write any point in a convex set as a sigma additive convex combination of the extreme points, and therefore this would be some kind of instantiation of Choquet's theorem. Isn't it just enough to have Choquet's theorem?
Well, the thing is that the fraction capacity is taking the supremum of all those measures.
Yeah, and so not just any representation, just taking the supremum.
Right, because then I have a unique.
But it shouldn't matter. If you can take any representation, is the supremum also a representation? No. Supreme is not a representation.
Well, it's not a linear representation. Like it's not an additive measure.
No.
I don't know if it's better to think about a simple example to make it concrete. So if you imagine that you have, let's say, a square. There you go. Right. If I pick this point, right, I have, let's say, like, okay, yeah, we can write the whole fraction capacity, A, B, and C, and D, right? And this is our E. Then F, like the fraction capacity of E for A is equal 1/2, which is also equal to the fraction capacity of B, and I'm not going to repeat it, then C and D, right? And then the fraction capacity for A and B. Well, let's do A and D first because I can do that right away. So for A and D and for C and B is clearly 1 because I can make E as a convex combination of A and D and C and D and C and B. And now the question is the fraction capacity for two, for let's say A and B. Okay, so I think it's still 1/2, right? I can't do better than 1/2 because any point that I take, I'm gonna take the opposite point, and so it's still 1/2. Okay, so this is 1/2 for all the sides. So A, C, A, and so on. And then for 3 points, instead, for any 3 points, we're gonna have 1.
That is the fraction.
Yes. So this is how it would look like.
Can you maybe explain in a bit of a detail how you're computing this?
Oh, yeah. So if I take A, then I can write E as a convex combination of A and D
Mhm.
as 1/2. And so since I can write E equals 1/2 A plus 1/2 D, I know that the fractional capacity is at least 1/2.
And
And then
you're
the
finding
point
the
is that
supreme.
if I the only other points that I can take are things that are in closer to E on the same diagonal, and therefore the coefficient would become smaller. And so the supremum is the one where I'm taking the farthest possible point, which is D, and therefore I know that the 1/2 is the value.
Okay, and if you do this for, I don't know, C, point C,
For the point C, same thing. I need to find all convex combinations with C. And so I have to be on this line. And again, B is going to be the furthest point. And so I have that E is 1/2 C plus 1/2 D.
okay. Can you write the formula for the measure?
So F the cap of E given a set A is equal to the supremum of P inside 0, 1, such that there exists an A in the hull of A and a B inside the whole space with PA plus P bar B equal E.
Thank you.
So this is like a possibility measure.
I don't know what that is.
So you seem to be taking so you seem to be taking the supremum of something, of A, right? Because you can take your supremum over of the existence operator comes outside as a supremum, right?
The existence operator comes outside in what sense?
So you have your supremum over P,
Yeah.
but inside your P, you have this existence
Yeah.
quantifier, and that will come out as an extra supremum, right? So you get the supremum over all A.
Yeah, you can do the supremum, sure.
So in some sense, this F cap will be, if you can define if you fix a point and do that.
Actually, that's how we define in the book first.
Yeah.
We define the fraction for a single point, and then we.
So then you extend it through the supremum.
Yeah.
But that
On
means
the
that
convex set.
your functional, the idea is that the functional of the set is the supremum over the elements of its hull.
Yes, yeah, that's exactly what it is. Yeah.
And so that's what we call typically a possibility measure.
I have actually defined that construction, and I'm rediscovering things.
Yeah,
Okay.
so this
That makes sense. This is the highest possible fraction.
yes,
Yeah.
yes. So that's what we call a possibility
Yeah.
measure.
Okay.
That might help. I never realized that this was a possibility measure.
Yeah, I mean, here I had done some like linear programming for probability if you want to read it, just to show that how this is computed with for 1 point. But yes, at the end, what you are so you are defining a support probability. So yeah, it's in there.
Okay, that could help. Well, that will ring a bell to you also, I think, Susanna. It's a possibility measure. Okay. In that case, and the F then? What do you want the F to do?
So now the F, you can imagine it as
Just a second. When you say F restricted to X, you mean like here, F computed only on the streams ABCD.
Yeah.
So this is like a Choquet representation result that you would want, right? No?
Yeah.
Find it in terms of the extreme points.
correct.
We still take the hull, so you have to really think about the elements inside.
Yes.
But it's all encoded now in terms of sets of extreme points.
Yeah, but even in Choquet, when you're you're doing the measure on the extreme point, it's kind of like you're putting the how
And there is a very simple expression for doing if it were the Choquet integral, there's a very simple expression for expressing the Choquet integral of a possibility measure. It's almost trivial. But that would also help you in showing that it's not the Choquet integral that you want.
and know why it fails. Yes. Okay. In fact, we can go. So it might be that the definitions that I have now, I'm curious because I defined this idea of having a function of on the convex space and then taking the supremum on the convex hull. And so if that has a name in the literature, I'm happy to just use that. Because even the what's it called, the state capacity is done in the same way. Because you have the exponential of the entropy of a single point. And then you say, when I have a set, you take the supremum on the convex hull for that function. But it's not from 0 to 1. So I don't know if a possibility measure has to be from 0 to 1.
For Wikipedia, yes, let's see.
Get the chapter of the book where I do that because so it's one of those things where I thought it would be easier to give the whole definition instead of breaking up in two pieces, but now you're telling me actually the way that I define it is better because breaking up in pieces. So.
No, it's a special possibility measure because the hull intervenes also, right? So it's not just the supremum over the set, it's the supremum over the convex hull of the set, which makes it a bit more complicated.
So here, like if you want, this is what I define. So let's say that you have an f from E to R, and this is just a function, it doesn't have to be affine or anything. And then I basically say that you have the convex supremum of f as defined that you give me a set, and I get the supremum of the f on the hull of A union some f naught, where this f naught has to be less or equal to the infimum of the whole space. And so you basically, like, you explore the convex set and you say, okay, always give me the biggest one. And then I need a value for the empty set, and the value for the empty set is lower than the infimum, so that the whole thing now is increasing, is monotone.
You could get rid of that last condition by just defining the value of the infinite set. So by defining the increment to be the smallest value that you can attain.
Right, but sometimes I don't want it to be that. So for the state capacity, I always want it to be zero,
Right.
even if there is a minimum that is greater than zero.
Okay.
Hugo has a question in Zoom. The convexity constraint seems a bit strong and appears to suggest the observables are limited to linear spaces.
These ones, the linear functionals have to be linear, yes. These one have to be linear. Like because those are basically expectations, so they have to be linear on the ensemble space. This one does not have to be linear.
Maybe it's a bit like those are what we call it statistical quantities. And
Yeah, there's statistical quantities and so on.
it's not, but in general, there are what we call the other ones again. The other quantities that are not statistical quantities.
Oh, just call them quantities.
Quantities.
And so the nice thing about this, anything that follows this pattern is increasing, obviously, and it's continuous from below. And now, what happens, as you were saying, that we define the fraction of A with respect to E as being the supremum of the probabilities from 0, 1,
So I think that you want to get
such that there is a B in E, that E equals
so basically
EA plus E bar B.
yeah,
So this is exactly what we were saying before. We define it first on a single point, and then the fractional capacity of the set. It's simply the CS, this convex supremum of A, where F is the fraction. And this is the fraction capacity. And similarly, the state capacity of a set is the convex supremum of the exponential of the entropy. Because this is just the supremum of the exponential of S of the hull of A. Union 0, and yes, and so like both of these are constructed in a very similar way. They are both now increasing functions continuous from below, and then you can prove the subadditivity and so on.
Quickly comment that, yeah, for non-panelist participants on Zoom, can also raise your hand and then we can unmute you if it's easier to ask questions that way than in the Q&A. So on a higher level, there's a very delicate balance between the completeness and consistency of any theory. In that sense, is the assumptions of physics theory more focused on the holistic coverage, completeness, or on the rigorous consistency of the representation? Hard to imagine covering both. Love the idea of the formalization of physical observability on a new theoretical framework, just trying to get a sense of the ultimate desirable outcomes beyond addressing open problems.
So for this approach, where we're going from scratch, we want to be like thorough and understand where the pieces are. And whether we don't cover everything, that's fine. The important thing is that what we cover, we have covered in a way that we can say it's done. Right, so that we once analyze this and we find that there are these measures make sense. Like these are things that we can always define and are always well defined. And now it's a matter of playing around with them and see if we can find useful, useful, if it can be used as useful tool. Then whether we don't catch all of physics, that's a separate question, and that's more for the reverse physics approach, where we try to figure out what the macro pieces are.
Yes, we have the reverse physics top-down approach and the physical mathematics bottom-up approach, which could really cover the very briefly at the very
but
beginning of this document.
We should stay on topic, otherwise it becomes distracting.
So if you had, is my argument correct that if you had any precise probability below that fact bound?
Mhm.
So for any precise probability, that integral would work because of the Choquet representation theory. So the idea was you have a precise one. You don't have a precise one there because you're selecting the supremum.
Right, I have a bunch of them, yeah.
But suppose you had a precise one.
Yes.
Then it would work.
They would just be a Riemann integral.
Yes, and it would work because then it's the Choquet representation.
Correct.
Right? So you have that equality for all the precise probabilities in there,
Yes.
right? So in other words, if I took the supremum of all those precise probabilities,
Yes.
I would have the upper expectation there. So
Yes, you would
was
have the upper
wondering
expectation,
I
yes.
was wondering if you could just take natural extension as an integral. Natural extension being the way you get somewhere through linear programming. That's you also define. So you have something that is defined on set function. It is an upper probability. So there are bounds on linear probabilities.
Right.
The idea is you do everything for the linear probabilities and then you take the maximum again, right? So you go through the inner envelope. That is one. It's like a dual a linear program that you follow. There are dual ways of doing it. That's not really important. But since you get the same result for everything inside,
We do get the result
for everything inside. That then it seems to me that if you do that and then afterwards take the supremum, you will still get the same result.
Right, but then I would need to know what are the correct Choquet representation.
Yeah, well, it's
Because I don't know what they are. If I just, I don't see how so suppose I just give you this, right? I guess just give you this set function and I don't know anything about this convex set, right? I just know that there are A, B, and C, and D. Can you figure out what are the
Value.
we take the natural, yeah. I need to think about this a bit more, but
so you think that there is a solution, and that's what I hope, that there is a solution with common
well,
tools.
there's an integral integral that hasn't been mentioned yesterday, I think, and that is the one associated with what we call natural extension, which is what I just described, right? So the idea is there are other ways of doing this, but the simple idea is you do it for all the precise probabilities, you take the integral for the precise probabilities, and then you take the upper envelope.
Right, this is the thing, the point I'm trying to understand. For that integral, you need to have the set of all the precise probabilities.
That dominate or that are dominated by your upper probability.
And you have it because the fraction capacity, you can write it as a linear program.
Yeah.
That you have it. Now, can I ask you something? Can you go back to the integral? Because it's not really clear to me how you define this, the integral exactly with that f of x.
Like this?
Yeah, so here. So what do you mean with f of x of integrated with respect to fraction capacity? Because f of x is a fine function, no?
No, well, no, not on x.
Sorry, restricted to x.
Restricted to x,
Mhm.
there is no
There's nothing.
linearity on x. Like
Okay, so basically you have f, just you compute on the stream and then the f.
Yeah.
Okay, I see. Okay, what you mean. And then, okay, and then you are integrating with the fraction capacity of the same stream that you compute. Okay, now it's
Yeah.
clear.
Okay.
Sorry, it was not clear.
So here you would be, you would integrate on the 4 points.
Okay.
That's what it would be. If I had a circle, right? Then for every point I would have like a continuous function of the angle, and then I would be integrating over the circle.
So the only thing that we would need to know in order, in fact, is if this F cap is that a coherent upper probability?
And upper probability.
Once we know that, we can
Yes.
try the natural extension if it works.
But for each X, it is, no? Because it's, so depending on where you define it, I guess.
Yeah, well, but if you define the F cap, if it were a simple supremum, then I think it would be, but I'm not sure what because you also push in the hull
Yes.
in there. So if it were just the supremum of F for F in A, then that we would know that is a coherent upper probability. It's an upper envelope of probabilities. But what you now do is you take the supremum over F, where F runs over the hull of A.
Okay.
And that I don't know yet if that is still a coherent upper probability.
But
It might be.
it is because, I mean, I think it's still operated as a linear program. So it must be. It must be. Okay. In the, I don't know if in the finite dimensional, if you have some issue with the border or things like that, but when we write the linear program, I mean, the finite dimension should work.
So basically, the conjecture is that F cap is a coherent upper probability. And then this would mean that the integral is the natural extension or comes from the natural extension? Right.
So basically, in a nutshell, basically you can compute the integral for each probability, and then basically take the.
So I would
after.
basically I give you the fraction capacity, and how do you get the set over the probability on which you do the integral?
The fraction capacity define the set, because you don't take the sup basically. Okay.
Right, but okay. So if I give you the set over the probability and not the fraction capacity, then of course it's trivial. You just pick one, do the integral, and you're done. But if I just give you the fraction capacity,
yeah, you need to do that static figures, swap that integral and the sup. This is the question. No? Yeah, it's something that we need to think about.
because so one of the things that it's unclear to me, right, is that not every probability, or not even every non-additive, sort of pseudo probability, I don't know what to call it, a non-additive measure of these 4 points will be a fraction capacity. So if I give you, I don't know, let's see if I can make something that does not make sense. I give you, right, so let's say that I give you that A is 1/2, B is 0, C is 0, D is 0, and then suddenly A and D is 1, right? This would not make sense as a fraction capacity.
But because then you have the linear constraints. So your linear constraints, that is, I don't know where is the definition of fraction capacity. Maybe in the next. Yeah, that linear constraint.
Right, but the constraint is basically knowing the shape of the convex set. Okay, that's basically where it comes from.
But then basically that is allow you then to recover the fact that, for instance, in this example, the fraction capacity of AD is equal to 1.
Right, so I don't know if there is a way, so even saying that there is a way to know, simple way, to know whether given a space, a fraction capacity is like a particular non-additive measure can be a fraction capacity or not. Mm-hmm. Because so you have if you have a simplex, it's easy, right? Your simplex is the only one that are allowed are the additive measures. So if you have a simplex, only additive probability measures can be fraction capacity, and every linear and every additive measure, additive probability measure, can be a fraction capacity. There's a complete equivalence, right? And now that instead you have a convex space that is not a simplex, you kind of have a distortion of the geometry. but it's kind of like all the fraction capacity have to be distorted in the same way.
Yeah, maybe what we could do is, yeah, maybe we can try to understand first in the probability case, but when A and B are, or even on this example, it's up to them. And then try to understand the generalized things, yeah.
So is there a way? Yeah, no, okay, but when, so when you guys do and set constraints and so on, and you get upper probabilities, right? So can the shape of these convex set be effectively translated into the set of sure bets?
Yeah, sure bets. Or
Yeah.
the set of the bets.
Right, you say of the background, what you were calling yesterday, the background.
Yeah, so, well, this is what I think what you were explaining. If you have the set of probabilities, you can go back to the dual cone of the bets that are correspond to that cone. Yeah.
Right.
Yeah. So it's in essence all the bets that have a non-negative expectation for some probability. So
Yeah, no, I'm trying to understand how to shape. So for example, if, let's see, if I know that the fraction capacity on A is a particular value, I should be able to know that the fraction capacity of B can not be greater than 1 minus that particular value. Right, because otherwise I would be able to make a convex combination of A and D that is greater than 1 or something like that.
But you are saying so, because basically here now you have the formula for each point where you compute it. Let's assume that A is just a point in this case, the big A.
Yeah.
So in that case, basically for each point, you get an interval of probability that satisfy your constraint of PA plus.
Yes.
Okay. So given that interval through duality, you get basically the gamble, the set the code. Okay.
Yes.
And from that, then you know what basically you get the intersection of this code and give you the positive code.
Yeah.
This is the background. But yeah, so the question is of course how we manage this complex hull on A, because it's to understand. And yeah.
can I ask another question? Because I'm just wondering. So what you're doing with your F, because it is affine,
yeah,
is you are transporting the structure from your set E to R.
Yes. Yeah.
It's like almost an isomorph or an endomorphism. Yeah.
I'm concentrating, so it's
Yeah. So to calculate F of these, somehow it seems to me that you could use the same argument as what you do on the original structure, right? Because the mathematics is transported. So on the original structure, you calculate the F cap. Why don't you calculate the F cap or something similar on the real structure? Because it's transported anyway.
right. So the complication is going to be that each point is transported.
Yeah.
And so I will have different bounds, but you're saying maybe.
So in your formula there, you do it for the A's and the B's, but you could just as well do it for the images of
for
A's
FA
and
of
B's, and then do it in the real structure.
okay.
Would that help?
I don't know, but I can write it down as a thing to explore. I don't think we're gonna solve it here, right?
No, but it's just ideas that we generate.
Yeah, write it down and so to explore. Essentially, it's like push forward.
Yeah. And that is because you have a very special F, right? If
Yes.
if the F were not that special, it wouldn't be possible. But since I would use the idea that this F is like an endomorphism.
Yeah.
Or whatever it might
Yeah,
be.
it sort of preserves the linear structure,
Yeah,
like
it's
the
a
convex structure.
homomorphism.
So I put it inside and then see that maybe I get something.
Maybe transport all the calculations to the real numbers.
Yeah. I think we've done enough of this. Switch topic.
Yeah.
Marcel, we wanted to discuss how do we do probability measures on field.
Yes. Can you hear me?
Yes.
Okay. So the one example we worked out with ensembles and configuration space, where we paid attention to a bit closer attention to that, is the case of gravitational fields. And then what we made use of is the fact that over the space of metrics, so we're taking space-time and doing a 3+1 decomposition. So we have a Einstein-Hamilton-Jacobi equation defined on the slice.
Can you share?
And
do you have something to share that we can actually see what you guys are
good point. Let me see. I switch computers, and I have to see if I have this somewhere else. Let me check quickly. Let me switch computers again.
Okay.
Connect again and see if I can succeed now from this other computer.
You can connect from both computers.
I'll be on both computers and then turn one away, turn one off. Let me find the link again to connect.
One point earlier. I'm promoting you to panel S with the new connection.
Let me leave this other computer. Okay, this first step seemed to work. Okay, I think I can show some ideas, which I don't know how useful they will be, but let's give it a try. Sorry, I seem to be having some difficulties today, but do you see
Yeah.
the document I'm sharing?
Yeah, we see it.
Okay. So what we have with this approach of ensembles on configuration space is the physics part is described by a Hamilton-Jacobi equation, and then you have a continuity equation, you have a probability. In the case of gravity, you would have a probability over fields. And what you do is you have the space-time metric, and you do a 3+1 decomposition, which is shown in this 10.2. And you can derive, you go through a Hamiltonian formulation, then you can derive a Hamilton-Jacobi equation. And you have two constraints here. And what you want to do is introduce a Hamiltonian, an ensemble Hamiltonian, which will give you these constraints plus a continuity equation for this probability over field. So everything is quite formal, really. But it turns out that the second constraint, which is the momentum constraint, is immediately satisfied if this function if this functional s is invariant under coordinate transformation. So this can be ignored, and you just have to worry about an ensemble Hamiltonian that will return equation 10.3. So if you remember in the for particles, you had an ensemble Hamiltonian, which was basically an integral of the product of the probability plus what was a Hamilton-Jacobi equation. Now, this means that you need to define some measure over the fields. And in the case of gravity, if I go back now to this equation 10.3, when you write down the Hamilton-Jacobi equation, and the same thing comes up when you write down the Wheeler-DeWitt equation for quantum gravity, you have this supermetric called the DeWitt supermetric, which is a metric over the space of all
All metrics.
It's a can then be used to give you the structure you need to define a measure, because then what you do is you take the square root of the determinant and say, well, that's my measure in this space. But you see that there has to be this additional structure for this to work. And this is something that has been explored both in the Feynman formulation of gravity, of quantum gravity, and also for Regge calculus, where you do a discretization of space-time, and you also have like a Hamiltonian formulation, and you also need a measure. And it turns out that the way you define it is you consider fluctuations of the metric, and they take this form of equation 1010, where omega is not is a free parameter. And what you do then is you define then this measure over gravitational fields, equation 1012, in this way. And this comes from the work of Popov, that did this work, I think in the 60s or 70s. And it turns out that you can calculate, this is all formal, and then you can define the most general definition that is consistent with this condition, with a set of requirements is equation 1014. And then you can, what we did is we said, well, we're going to set this parameter omega to 0. And this is, in any case, what the choice that DeWitt did when he worked on this in the 60s. But our argument has been, well, if we have some multiplicative factor like this, we can always incorporate it into our probability over metrics. So what we have here is the advantage that there is some further structure, which is the DeWitt supermetric, and which allows us to at least attempt to define this measure here.
Okay,
Now, in our case, this was not very important in the sense that what we ended up with was basically equation 21, and we introduced some sort of variational principle, but this is very heuristic. Basically, we said we know how it works in particles, and if we do something similar with these fields, then we're going to get equation 20 and 21, and the first one is the Einstein-Hamilton-Jacobi equation. This H was defined before, and equation 21 has the form of a continuity equation.
So
And
specific.
what one finds is that if we take this seriously, that this looks like a continuity equation, then
Marcel, can you hear me?
I can hear you. Yeah, sorry, but it's not very loud, but yeah, I hear you.
Okay, so because I got lost way before.
Sorry about that.
So this is specific for essentially the metric. Like this is not something that can be generalized to any field or function space.
I think this this idea could be generalized if you have some sort of metric over the space of fields that you can define in some way.
So
If you have some symmetries.
Let me give you a much simpler example. Will you be able to do it for classical E&M, for just the electromagnetic field?
I think this should be possible, and I was thinking about that this morning. I think a good source for this type of metrics over fields, or about measures over fields, is the path integrals, because they need to define that one way or another. And I think one of the things that Popov did was bring in some sort of, he came up with this ghost and this way of dealing with gauge theorems, where you don't want to count more than once the equivalent classes of fields. And I'm not very familiar with this formalism, and I only was interested in gravity in this case. But the places where I found a lot of help was in people doing Feynman path integrals, who need some sort of measure that they have to define one way or another. And I think this is also has been done for electromagnetism, but I'm not sure. I think the work of Popov where he has these ghost fields, and he has some way of fixing, sort of doing a gauge fixing, might provide a way to do this.
Okay. So I was hoping that you had something similar, like that you had from a classical mechanics, where you had the probability of Q, that you really had something probability of a generic field. That's what I was hoping you had.
Yeah, well, in this case, there is a probability of a generic field. It's given by this equation 1014. This is what comes out if you follow this process that was done for Regge calculus or for
But H here is the metric tensor.
H is a metric tensor on the slice. So it's a three-dimensional time slice after you do the 3+1 decomposition. And yeah, this gives you a measure over these fields up to this constant sigma, which, as I say, we set to 0, and we have argued that we can set it to 0 because anyway, whenever we use this integrals, we have a probability distribution times some function of the fields, and we argue that we can incorporate this piece into the probability over the fields. But as you see, everything is by analogy to the case of particles. There is no rigorous mathematical approach here. And it would be interesting to see if something of this sort can be done for other fields, other classes of fields.
Yeah, so I basically I'm trying to understand what I'm trying to figure out is first I'd like to do it without gravity, is just what is the correct symplectic structure, Poisson structure to put on fields that allows me to generalize some of the things that I already have in classical mechanics. And that's basically what I'm essentially looking for.
Well, one possibility would be to go to take your symplectic space and extend it to a Keller space, and that is you require that you have some consistency between the symplectic structure and a metric structure, and you also have a complex structure, and then you have a metric. We did that for discrete spaces, for ensembles on configuration space. I could show you a little bit of that if you're interested.
Do you have it on particle mechanics? Because I'm looking for a structure that works in the mechanics case in sort of exactly an analog way in the field case.
It works in particle mechanics too. So we did it first for particles, and it uses the metric of information geometry to make this step.
That would be interesting, yes.
I could show you that because that was the third part of my talk, which I threw in there just in case.
Okay.
If you want, in 5 minutes or so, I can give you the basics of it.
Yeah, let's do that. That would be useful.
Okay, let me do that then. Showing now the talk. Do you see the presentation? Yes?
Yes.
Okay. So yeah, we looked into the geometry of ensembles on configuration space, and I do this here for the discrete case, which is simpler, but it also carries over to the continuous case. And our starting point is that we know that there's a so-called information metric, and that this gives us a metric of the space of probabilities.
So is this the Fisher-Rao metric, or is it a different metric?
This is the Fisher-Rao metric, yeah, for discrete cases. I wonder if I should just do it for the, well, let's do it for the discrete cases. So this is the Fisher-Rao metric. And and here's a little bit about distances and thing in Fisher-Rao. We don't have to go into that. And there's some, there's a way of deriving this information metric by Shenkov, where he looks at cases where you split up probabilities into larger spaces, like is shown in this diagram. And then he requires some consistency requirements and shows that the only metric that works is this Fisher-Rao metric.
Yeah, so the way that we recover the Fisher-Rao metric is by just looking at the negation of the Hessian of the entropy. That just
Okay. This seems like a better way to do it.
It's something that we can define also in quantum mechanics. You get the BKM metric, which is one of the way that they extend things. So that's kind of the point. We have a way to get that metric from the entropy, and also we have a way to get the volume measure from the entropy. So if these things have always to work in a certain way, that's
So what we said, well, we have in ensembles and configuration space, we have two canonically conjugate variables, which we call P, the probability, and S is the conjugate variable to it. And we have a Hamiltonian formulation, so we have a symplectic form. And what we would like to do then is say, well, we know the metric for the probability, which is one of our coordinates. Can we extend this metric to a larger space over both the P's and the S's? And we said we can do it, but we will ask for some consistency conditions, and we'll require that the space will have a Kähler structure, because if you have a metric and a symplectic structure, they should be compatible, and Kähler geometry does that for you. And we have here the Kähler conditions of how one should relate the symplectic structure to the metric structure to the complex structure. So what we need to do is find out here the metric structure and the complex structure, given that we know the symplectic structure, we use just a standard form of the symplectic structure, and that we know part of the metric structure. And what we say is that, okay, we know this matrix G here for the full metric, because we're going to say that it should be the Fisher-Rao metric, but we have to find the other ones. And it turns out that if you impose the Kähler conditions and assume that, then you can find specific forms for the metric over the whole space and for the complex structure over the whole space. And the only thing that you have floating around is this matrix A that is not determined by the Kähler conditions. But this is already a step forward, because from a space with a symplectic structure, you're getting to a space with a general condition. We took this so-called Markov mappings of Shenkov, which he showed are fundamental for information geometry, and extended them to a canonical transformation. So we came up with something that was a generalization of these Markov mappings. And these Markov mappings change the dimensionality of the space. And one can do that also with canonical transformations. There are ways of doing it, but there was also possible to do it without formally going to this formal ways of defining canonical transformation between spaces of different size. And it turns out that you can set this A equal to 0, in which case everything becomes very, very elegant. And then if you define a wave function by taking the Madelung decomposition of the wave function, and you calculate what happens to these three tensors, then you get precisely what you have in quantum mechanics. So you get this metric, which is the wave function times complex conjugate. You get a complex symplectic form, and you get just a diagonal form for the complex structure. So this, in a sense, is pretty much a derivation of quantum mechanics, a geometric derivation going from ensemble configuration space by saying, well, we're going to go from the symplectic structure to a Kähler structure. And if you take an A that is different from 0, then it turns out that you get the wave function in the way that it was done by this nonlinear gauge transformations of what's his name? Anyway, there was some work on nonlinear quantum mechanics where they show that certain theories are equivalent to quantum mechanics, and this is exactly the form. Jerry Goldman, and anyway, it's in the paper. But yeah, so the last thing you can do is you can look at which transformations are allowed, and you get the unitary transformations. So the whole approach comes together quite nicely. And then this comes from some work done previously where you go now to a Hilbert space and define a Dirac product using these structures. This was done by Kidd when he formulated quantum mechanics.
Case then, you would have a metric on the probability distribution over position, and that would still be the Fisher-Rao metric on the continuum, I guess. Some kind of generalization, infinite dimensional generalization of that.
Yeah, I can show you very briefly how that works. Let me find that. Because it's up to let's say oh, what is going on here? I think you can see this, right?
Like what can we improve on the?
Sorry, I'm looking for the continuous case here. This is all discrete. Yeah, for the continuous case, what you do is you consider the Fisher-Rao metric, and you consider it for translations, that is equation 6.6. And then by doing a change of coordinates, you can write the metric as 6.7, which is the Fisher-Rao metric, basically, here. And what you do then is you define here the metric. It's a local metric, equation 6.9. And then when you want to go to when you want to go to the Kähler space, you say, well, the metric, we know what the metric is in the upper left up corner, but we don't know what the rest is. And then you get, when you solve the Kähler conditions, you get equation 6.28 and 6.29. So these are identical to the discrete case, but now defined for the continuous case here. And the way we dealt with this functional A or function A, so we had here we just said that we use the results of the discrete case, and we'll just have this function A equal to 1, and then we get everything that we got for the linear case, but now in terms of continuous variables.
Okay.
So it translates into the continuous case, but it's no longer that doesn't anymore have the rigor that it had for the discrete case, of course.
Yeah, sure.
But there's probably ways of making this rigorous. I'm just seeing if there's anything else here that would be of interest. You also get the group of unitary transformations in this case. If you,
Okay, thanks.
if you,
I can look at it in more detail then. I have the book. So.
Yeah. But I think that the message is that let me see if I can stop sharing the.
Yeah, you already stopped sharing.
I stopped sharing already. Okay, good. I think the message is that it might be possible, knowing that we have a metric on the probabilities, to go to a metric on wave functions, for example, or on this canonical conjugate quantities PNS, by going to a Kähler space. If you already have a symplectic structure, and you know part of the metric because you know the metric, the information metric, then this trick might work again for other theories.
Yeah. The complication is always that we have distributions over the full configuration space, like the position and momentum, and so you're using the fact that you're using only on position, and that's how you get the metric on that, and so on. So
right. Because on phase space, there's no natural metric. But on the other hand, you can go to a Kähler space starting from phase space.
So the way that I can see connecting to you is basically, instead of looking at the probability itself, once I pick a set of, what do we call it? I pick a configuration. At that point, I'm in phase space, so it doesn't even have to be position. It has to be just a set of 1/2 of the Darboux variables, and I can do the marginal on that. And then what your work shows is that once I have the marginal of that, I should be able to find a conjugate quantity to that marginal, which would be kind of the S relative to those variables. And then on that, I should be able to find something. But that might even be the thing to do because like the wave function is essentially set up like that, so that there might be an interesting way to sort of look at the thing in these different ways. And depending on what I'm doing, I'm going one and the other. So the only thing is that I'm pretty sure is that once I get the marginals, I lose some information because the joint distribution will have more information than the marginal and the S, because that's how functions work. But
Yeah.
again, it might still be a useful thing to look at. So
I found the paper by Kibble on the geometrization of quantum mechanics very useful.
okay.
And then this was further developed by Ashtekar, probably that was in the 90s, where he really gave a geometric formulation of quantum mechanics, where he uses this Hamiltonian formulation with a symplectic structure and a complex structure, and also a Kähler, all put together in a Kähler manifold. And there's a paper must be about 1996 or so, from Ashtekar on the a geometrical formulation of quantum mechanics.
Cool. So I'm familiar with the sort of the Kähler manifold, part and so on. So that I have seen, and what I would be, I don't know. Are you aware of anybody that did that, but on the space of density matrices? Because the suspicion is that the space of density matrix should be a foliation of Kähler manifolds, and as you go inside, that you increase the entropy. The entropy essentially, in some sense, it's one of the variables that foliates this. So
Yeah, this I haven't seen that type of work, but this might, maybe you can use a trick if you have yeah, but you need something canonically conjugate to it.
yeah. So
No, I'm not aware of anything with density matrices.
yeah. So that's basically what I'm looking for. I'm looking for the space of density matrices. The space should not have a Poisson structure that is degenerate in the direction where you go in, right? So if you're moving at the same space of entropy, then you're kind of like, you're essentially working on some type of extreme points moved a little bit back in. It's just that things that get a little bit complicated, but that should be the idea. And so I should be able to have this sort of a Poisson structure on the density matrices that basically is aware of where the entropy is increasing or not, because all the non-degenerate direction are the ones that are conserved. And then on that space, I also have and so on the shells of equal entropy, I should have a symplectic structure. Like I don't have it across, I just have it there. And then
there.
I should have a Fisher-Rao metric type thing, the BKM.
Right.
Within, because I can go any direction now, as long as I'm not on faces, whatever. But if I am in the bulk and I'm moving around, I have a notion of distance. And so now what I'd like to generalize is that notion of distance that I have with the symplectic structure or the Poisson structure that I have on the whole thing. So that's the part that that's the part that I would like to generalize then in classical mechanics as well, so that I have a Poisson structure on the space of probability distribution on the joint, and then I also have, and so given that I have a Poisson structure, I will have a symplectic structure when I am moving in the non-degenerate direction, which I think should be all the ones where entropy is conserved, and then I still have a distance, which is this, generalized Fisher-Rao matrix in infinite dimension. And then I would hope to expect that there is some kind of Kähler structure equivalent to this thing, but I have no idea how to do it. So, okay.
This Hilbert space formulation that I showed yesterday, where the classical particle is a function of Q and P, can also be given an ensemble interpretation, formulated as ensembles on phase space. And and I'm wondering if there it might be possible to do this trick again of finding a Keller structure for particles that live in phase space.
Yeah.
But I never tried it, and would be interesting. It should be possible to do that now that I think of it. But I'm not sure. This might also help with this for the quantum mechanical case.
Yeah, I think that there should be a superstructure that is common for both. That's basically should be the idea. And so the way that I see the distribution configuration space is that it's kind of let's say a hybrid that it's a little bit in between, because effectively you have the pure state in quantum mechanics, and you have some type of distribution in classical mechanics that are not the pure state, because they're not the points of position and momentum. They're not the full distribution of phase space, because you only have the marginal position. They're basically the happy medium that allows you to make the analogy for the pure state of quantum mechanics very well, right? But I think there should be something that it works even more similarly in the bulk of and I feel that there is there. I don't know quite.
Yeah.
What the
No, it seems that this structure should be more general, that one can work them out for the general case and not just particular examples. Yeah, it's very interesting.
All right, it's about time for a break. Do we want to decide the next topic of discussion before we break?
Sure.
That might be useful, especially for people attending remotely. I can share the topics again that we came up with yesterday. Just
So we did
get
those
the
two.
first two. Again,
Especially Marcella and Susanna, if you have some topics that you'd like to discuss.
Susanna, is there something else you would be specifically interested in?
The topic of the background here, dealing with it in the infinite dimensional case, or this issue of whether permutations are enough to define the background, that's something that I would be interesting. I don't think I can contribute, but I can certainly learn from a discussion about that. But if there are other topics that are more, more urgent, of course.
Those are interesting to me as well, and we could start with the permutation thing. That's gonna probably be easier and more concrete. And Hert, you can walk us through the derivation and where.
You mean for the symmetries from indifference, or are permutations enough?
Our permutation for the background.
Yeah.
Because that's more concrete, and then once we talked about that, we can go and understand how the symmetries work for the infinite dimensional cases.
Okay.
Okay.
Susanna, do you have any comments?
Well, for me, everything would be new and interesting, but maybe I was not yesterday for the presentation of Alessio, but maybe something about entropy would also be very interesting and giving some new options for me.
So the link between the assumptions of physics entropy and Alessio's entropy that he mentioned.
Okay, perfect. So we will come back in 30 minutes after our break.
Good.
Sectional, yeah.
Mhm.
And since it's closed under intersections, it's gonna work.
But yeah, you could try this work so even with the Bernstein polynomials, because then you have, you know, the Bernstein polynomials, so the definition of positivity being in the corner with the coefficient positive.
Yeah.
So then I think it could be another way to see that this approach works there too, because there basically you have that.
For the precise ones, yeah.
Yeah, because you for some theta, no, you may have some. I don't know how you define it in that way. I need to think about like some coefficients that are positive, and not all.
You need a Bernstein expansion to be non-negative rather than a polynomials, right?
Yeah,
That's the idea.
Yeah, the Bernstein was negative. Oh, no, what was that?
So what are you sure? What are you sure of? You're not sure of the theta.
No.
You're sure of
Okay, so.
You know the
let's see,
sequence.
Let's go. So we're set up.
Yeah.
Shall we start with the entropy discussion, which I think is gonna be more contained? How do we want to do it?
I guess maybe then also we define the entropy, for instance, in the quantum mechanic case.
Yes, so let's do it like this. Yeah, so you stop sharing, let's see if I can, at this point, I might share from my laptop and take the latest book draft and comment on that so that I don't have to type a lot of stuff. So, and the book is there. Okay, so you should see. Okay, well, I only wanted this. What's the one line shared? Okay. No, I'm sharing the screen.
You're sharing
No, yeah.
you're
okay.
sharing the browser. Right?
Yeah. And now where is my? It's completely gone. Oh. Oh man, let me do it. Like, which browser am I sharing at this point? Yeah, I'm gonna.
Stop sharing.
Yeah, but I don't know.
You can stop sharing.
I can't stop
Fine,
sharing
yeah.
because I can't find. So. I just whatever. Too many things. How do we get to the thing again?
Escape. Try.
Oh, there it is. So, I had two windows that look the same. Okay, so this is the definition of the entropy that I showed you yesterday. Okay, so these are the properties. So it's continuous, strictly concave, there is an upper probability and the mixture of preserved. And then there is a proof here that shows you that this I has to be the same, has to be the Shannon entropy. And the way that it works, you essentially assume that there are a bunch of orthogonal elements. And then you say, I have n Actually, here you go. You pick n times m elements that are orthogonal to each other. And then what you can say is that, well, I can calculate the entropy of the mixture of all of them together, or I can calculate the entropy of m mixed together and then the mixture of n times.
Yeah.
So if you do that, then you find that this entropy increase has to be the sum of the entropy increases when you're mixing m and when you're mixing n together. And so this, with the Cauchy functional equation, tells you that if you have uniform distribution, then this entropy increase has to be kilocalorie. And then you say, now I have a rational distribution. If I have my p's are rationals, I can find an m that is the least common denominator.
Yeah, you can do the same.
And I do the same. Right? And so when you do the same thing, you find that you have a uniform distribution, where is it? Here. And you have another uniform distribution here. And then you turn the crank and you find that it has to be P log P. And then by continuity, it's like the simplest proof that I was able to find. And you can also do it graphically by looking at the boxes. And so it's. And so the cool thing is that this is
it
telling
turns
you,
products into sums in a sense, right?
Yeah.
Right. That's the idea.
it's kind of similar of the original Shannon idea, but he didn't do this trick of just decomposing everything in uniform distribution. It's basically what I'm doing, which is much simpler than what he does. And I am not assuming the type of space that I have. Because what happens in all these things is that you have the entropy of something, which is then the entropy given by the maximal mixture and the entropy of the sum of the entropies, the average of the entropy of the other things that are there. So you have this and this, right? These are going to simplify, essentially. They go away. Mm-hmm. And so you don't care what these things are, because you're always looking at the entropy increase. Like that entropy is always a difference with something. So whether you're making a difference between the quantum states, mm-hmm. classical states, continuum, discrete, it doesn't matter. It's always a difference.
And from here, then how can you derive the von Neumann entropy? So
the von Neumann entropy. So suppose now that you are in I don't think I've written it down. Yeah. So suppose now that you have a density matrix.
Okay.
A density matrix can always be decomposed as the sum of orthogonal pure states. And then you know that you're maximizing the entropy, so that you use the only thing that you don't know, right? Let's go back to the definition. So you know that they're orthogonal. Mm-hmm. So you know that you are in this case with the equal.
Okay.
Because they're orthogonal. And so what you don't know, and you have to assume from somewhere else, is that the pure states are entropy zero. And then you find that the entropy of the mixture is simply the Shannon entropy of the decomposition in pure states, which is the diagonalization and so on.
So but here is that you exploit the spectrum decomposition.
Yeah. So in both classical and quantum mechanics, every ensemble can be decomposed in orthogonal pieces. So once you know this entropy increase, you can know the entropy of every mixture, because you just decompose it in orthogonal things, and then you say, this must be it.
But then you have the problem that you don't know, like you were saying yesterday, if you restrict the extremes in a way that are not orthogonal, or they're not like, in the simplex, like you do the smallest triangle, then you have a problem here.
I have a problem because this thing here only tells me something if you have orthogonal elements. So if you don't have orthogonal elements, I can't prove that the entropy in the bulk is the restriction of some Shannon-like entropy. I just know that there is an upper bound. And in fact, what you can do is put other functions that satisfy the bound and that might have completely weird properties, which I suspect it means that I'm missing another axiom. So I suspect that there is a stronger axiom than this that recovers this orthogonality, but actually tells you something about the 3-point case.
I see.
Let's say the biggest hope that I have is that if you remember, we can define this mixing entropy, which is just how much the entropy increase based on the entropy of the region, right? And this thing is continuous, non-negative. It's 0 only if A is equal to B. It's unit bounded. It's less than 1, and it's equal to 1, and it's 1 only if they're orthogonal, and it's symmetric. And so the only reason that this is not a distance is because it does not satisfy the triangle inequality. Now, in the classical quantum case, this thing is called, it recovers the Jensen-Shannon divergence. And the Jensen-Shannon divergence is not a distance, but it's the square of a distance. So my suspicion is that I might need to have enough axioms to show that the mixing entropy has to be the square of a distance. But I don't know how to do it. So there is a property that the squares of distances have, which you can define something called a quadrans or quadrants, and that thing has always to be positive quadrants is the square of a distance, and so there is a property that quadrants have to be to satisfy, but it's very complicated, and I haven't tried to unroll it and see. So I'm pretty sure that currently this wouldn't satisfy that inequality, because as I said, I can create counterexample that make this thing essentially. This is going to give you open balls, and if the open balls are not convex, then you're pretty sure that can't be the square of distance function. Right? They have to be convex at least. In fact, I suspect that there should be at least enough a structure there to force the open ball given by this to be convex. And I do think that it wouldn't make sense physically to have them not convex, but I can't find a tight justification to, right now it's just my feelings, which is not enough. And
the bound and the convex structure that we already have doesn't force that.
No, it does not force that. Yeah, it's surprising, but
How does this solve the extreme problem that we said before? The entropy.
So if we had, if we were able to say that this, for example, were the square of a distant function, then I would have a lot more control of what happens between 3 points. Because, for example, I wouldn't if these are 3 points, the ball that I have to make are convex sets. So you have a lot more.
You need to satisfy the distance inequality.
The triangle inequality, it would be the square of that triangle.
Would impose some restrictions.
Yeah, and I think that might be enough to say a lot more things. But that's an open problem for me, because it's one of those things that anybody who defines entropy, they typically define it on top of the probability, and then they have this automatic assumption that if they're far apart, they're orthogonal. Because they put these probabilities and they put them in the Shannon formula, and therefore that's what it is, right? Because they don't have the sense that these two structures, the convex structure and the entropy structure, are really disjointed. You can kind of put whatever you want, well, within some limits that we have seen, right? And so I don't have any examples, and even the proofs that show that the quantum Jensen-Shannon divergence is the square of a distance function are those horribly complicated unenlightenment proof where they don't just use it for that. They have the families of with the alpha of all the entropies, and then do some derivative on the parameters and so on, and then they prove something. And so I can't get a sense of what is actually going on. And so I don't know how to generalize. Yeah, since we're going entropy and we were talking about derivative, like the what's it called, the metric tensor before, the other things that I have is that if you assume that the entropy is differentiable, then you can define a norm of a variation based on that mixing function. And then what you find is that the sort of the distance that you have here from this norm, you can define a sort of a metric tensor like thing, which is not a metric tensor because these are infinite dimensional, right? So these are variation on infinite dimensional thing, but I can still define this object. And what you find is that it's the minus the Hessian of the entropy. And that recovers here. It recovers the Fisher-Rao metric.
On probabilities. Yeah.
Right. And it recovers the BKM metric in quantum mechanics, which is one of the generalization of Fisher-Rao. And this is the proof that took me a lot of time to understand which one. Yes. There are many generalization of Fisher-Rao metric in quantum mechanics. They all agree when because the variation may not commute with the point that you are at. I think in classical mechanics, the variation always commutes with the probability distribution. Mm-hmm. If you make a variation of a density operator, it may or may not commute with that. And all these metric tensor agree when the variation commutes, but they disagree when the variation does not commute. And so it took me a while to have this derivation done correctly in the case that it does not commute. And then there are these horrible formulas that you can use, and then I know that's the right way.
So the log row that's defined through the eigenvalues, right?
Yes,
Yeah,
those
that's
are defined
typically
through the eigenvalues. And that's exactly the problem. When the variation does not commute, it's not just a variation of the eigenvalue, it's more complicated. And so you have to use this formula, which is a formula that basically it's the variation of the log. It's this formula that I got from I wouldn't know how to rederive this, unfortunately, because I like to be able to rederive everything because I don't trust anything at this point. I went, so the first pass of this derivation, I basically looked at what people were doing in the literature and just mimic them. And then I later discovered that they were just doing things that didn't work.
Just doing it.
Yeah. And so now I'm fairly confident because I was able to go from each step of this and understand what were the properties and the theorem that I'm using at each step. So okay, I'm in the realm of validity of each thing.
So you get that -1 twice, so like the what that was minus 0.5. I don't know. Yes.
The other side, this is the only thing that I don't understand. Like, I don't know how you get to this. That's magic. Yeah, the other part I understand. So this was this is basically the thing that people were doing wrong, is that when you have the trace of a function of x plus a variation, then it is the trace of the derivative of x times the variation. But that only works when you're taking the first variation. When you take the second variation, you have something else in front, and now you don't match the form anymore, because the first variation may not commute with the logarithm. And so you can't do the same trick again. You can't. So if these commuted, then you could still take the derivative of the logarithm and you would be happy.
Yeah. Okay. Could you just go back to the definition of the entropy again? Please. I'd really like to understand that.
Sorry.
So it's a functional on mixtures, right?
Yeah.
And it's super additive on these. Well, super.
It's strict concavity. It's different than.
And the equality holds only if they're equal. If
Yes.
and only if.
Yeah.
Okay.
Basically,
So it means it must increase as soon as you mix.
yes.
Yeah.
If
So
you're
that is
mixing
the
things that are
intuition. The intuition of why mixing increases increases entropy.
Yeah, it's you're increasing the variability. As soon as you're mixing two things, if you're mixing two things, you're not increasing the variability, then you're just mixing the same thing with itself.
Okay, and then you have a bound, and that gives you the Shannon entropy.
Yes, you later find that this bound is the Shannon entropy. So the trick here is that you're assuming that this is a universal bound, that it's the same for all ensemble spaces.
And then you can prove it using your proof.
Exactly. And then you say, well, suppose that you have an ensemble space in which you have countably many orthogonal things, then that has to be that. And since it has to be that for that, it has to be.
And your definition of orthogonality was in terms of?
You saturate the upper bound. So
So you define orthogonality through the
upper bound.
through the entropy?
Yes.
And it's then only in that case that you only in orthogonality that there is this preservation. No, okay. Yeah.
So basically, the idea is this: orthogonality means that you're mixing things. You have your two procedures that are spitting out instances, and the instances are so different from each other that as soon as you set up this multiple times, as soon as you see one instance, you're able to see, oh, you use that preparation instead of the other preparation. Which is exactly, information-wise that what you do. You have the two sources, and you want to be able to know, oh, you use one or you use one. That's how you pass information. That's exactly it, right? Yeah. And so that's also the case when you're mixing that you get to the maximal entropy increase, because you're mixing things that are always completely different from each other. So every time that you're mixing, you're maximizing the variability.
Okay, but so in your statement, if the equality holds, you mean if it holds for all p star, p bar.
Correct.
Okay, that's important. Okay, yeah. So whatever mixing you do,
it's always maximized. Yes,
it's going to be maximum, and that's why you call them orthogonal.
Yeah, you call them orthogonal because it literally recovers orthogonality in function spaces and density meters.
Okay. That covers it.
It gets you that. Like if you think about it, you have in classical mechanics, you have two distribution with disjoint supports. Then when you are mixing it, you're gonna have the entropy, like the average of the two entropy plus the Shannon entropy of the probability of the two things.
But in theory that you are not too clear about the extremes of the mixed space at all. No, it's because that could be something that I mean you could exploit, to be, I don't know. I assume that the entropy of the stream is 0, for instance, or something like that. You're not assuming that.
And I have to do it because in a classical space, I don't have the extreme points because there would be Dirac delta functions, and that those are not there.
Okay, I see.
So you don't want to talk about them? Anyway,
I don't want to say that they're ensembles.
why would you?
Exactly. Yes.
Well, maybe you could do some sort of like, I don't know, limit or something.
Right,
could
and
be
that's my
limits.
problem is understanding where to make the limit, because I think I have to make it. I think I need the linear functionals because this is something that I worked for like months, and then here there are these open problems and lesson learned that have all the things that I was not able to do with all the failed attempts. And one of them was, okay, suppose that I give you the space, how can you recover the points? So suppose I give you the space of all the probability distribution over phase space. Can you recover the points? And what I figured out is based on the topology and the convex set and the entropy, the answer is no. Because you could imagine to have a real line, actually, even better. You have a circle, you have the real line, or two copies of the real line. Okay, so because you're just removing one point, and because you can't put distribution on that one point, the sets of supports and they're completely like there is a homomorphism between them. So you're not able to recover, even if I give you the space of all the distribution, you're not going to able to recover the topology of the three things. They all look the same. And so I need something else. And I think that's the linear functionals at this point.
Well, what do you mean linear function on what?
So if I have my probability distribution on position, I will have the linear functional of position and of position square.
Okay.
Right. And now the delta functions are going to be exactly the limits for which the variance, so the position square minus the square of the expectation of the position, it goes to 0. So I can see that as a limit, not in the ensemble space, because the limit does not exist in the ensemble space, but I can see it in the limit of the vector space of the outputs of this linear function. But I don't know how to pick the correct linear functionals yet.
Because the embedding that you said through the cancellation that is replaced with the entropy doesn't.
I don't know if it's continuous. I don't know even if I said that. Well, I now have that the space of linear functions. How do I pick the correct one? What is the right property on these things? I have no idea. And it could be that then I need this, the algebra, because the algebra picks out position and momentum as being important things. And so maybe it's I want to use that. I want to use the variance on those to go to 0. And that there is a link to that entropy, to the entropy anyway, because if the variance of x and p goes to 0, I am selecting points, but this is not going to work in quantum mechanics. But in quantum mechanics, you don't really have points of phase space, so that might not be so bad. Yeah. Okay. Go back and forth.
Connect to what Alessio would present yesterday.
No, but yeah, I think we discussed because what, so I was thinking about the theorem that says that, when you have these symmetric cones, then for all of them, you have a spectral decomposition, and then you can always define the determinant, the log, and then the entropy. But I guess, again, this assumes that the extremes are already defined, so that is something you don't want to assume.
Yeah.
Yeah.
And you might want to.
Could you explain it a bit?
Oh, yeah, go ahead.
Yes,
One? Or-
it's
Yeah.
just that.
So how is the so how is the relation here between that and?
So, okay,
yeah.
so basically, okay, so you have these 5 cones, okay, that are symmetric, and for each one, okay, yeah, you can prove that there is a definition of spectral decomposition. Okay, so you can have basically eigenvalues, and when you have that, you can compute the log by doing the spectral decomposition and then doing the log of the eigenvalues. Okay, so once you have these, then you define the, say, entropy by taking the inner product of the linear form there, and with the matrix, the log of the matrix.
Mhm.
Okay, that will be like, for Neumann,
Von Neumann entropy.
generalized to all that codes. Okay,
Yeah.
but to do that, you're assuming you're doing a spectral decomposition, and so you have like extremes, the orthogonal extremes, and so it seems to be that it's something that you don't want to assume to have that.
Yeah, okay,
Because
it goes the other way around.
Yeah, so means basically, so if you want that, you may want to focus on cones that are not symmetric, because you want to restrict, for instance, the mixed space of the cone. And in this case, those, I mean, the entropy with that definition is not well defined, because the extreme will be outside it somehow, spectral decomposition. So yeah, I'm not sure really.
Yeah, but then you said you can define it mathematically, but it might not correspond to the physical entropy of the system that you have there.
Yeah.
Okay, we move to the permutations and collapse.
Okay,
You want my tablet so that you can write?
yeah, perhaps. Okay.
Okay, here, share. Screen, specific app. What app? One. Nine.
Okay. Thank you. So what I'm going to try to do is try to very briefly describe how you deal with symmetry in the context of what I discussed yesterday. So in the context of these accept desirability models, these couples of two models, right? So you will remember that if I have a model M, which is of the form, let's say, accept minus desirability. So this was the form that we were looking at. So the minus desirability is the rejects, right? The ones that you reject. Then there is associated with that a set of indifferent options, which is just the intersection of A. So the ones that you both accept and want to give away, those are ones that are indifferent. Now, suppose that I start out with an M. So these here are the set of indifferent options that are associated with your statement model. All right. Now suppose that you start with a statement model, and you now have an additional set of options that you believe are indifferent. So you already have made some assessment. You say, okay, this is my model, but then you get an idea that but there are other indifferent options that I would like to add to my model, right? And there's a way of it, because there's a notion of conservative inference. So I can add statements together and look at the most conservative combination of these things. That's typically how you do this. So assume that I have another I. So let me call this I0 here, I sub 0. Now I have another I that I would like to add to, so there's a set of options that I would like to add, and for which I state these are indifferent. Okay, so this, I'm not going to do the mathematics, I'm just going to tell you how this works. So the idea is that if you do that, what happens happens is that you get a new n, where the acceptables are just the Minkowski sum of so the Minkowski sum of, so what you do is to your acceptables, you add the linear span of the ones that you thought were indifferent, because typically, well, since A is a cone, minus A is a cone, the intersection is going to be a linear space, right? So you know that for a full model, it will have to be a linear space, your indifferent ones, right? So that is, so this is how you do the inference for your models. You just to both sides of the accept desirability picture, you just add the span of the indifferent ones. So that is a basic idea of how you do inference in using indifferences, right?
So just quickly, all the elements in A and D, those are these real functions.
These are
functions,
real
right?
functions. We call them options, right? So whatever it could be measurements. It's quantum mechanical measurements. So Hermitian operators, it could be, or it could be functions.
But they always give me a real value, right?
Yeah.
And they take in something.
Yeah.
Good.
That is the idea.
And now I just said, okay, I'm indifferent about these, so adding this
about
to
these
what
options,
I accept, I should still accept
Yeah.
that.
Yeah. And
That
that's the
makes
idea.
sense.
So this is how you now. Okay. Once you know this is very simple. Now the idea is how. So now suppose this is the first idea. So how to do inference. There is another idea. Suppose. So. And a second, so this is the first idea. The second idea to get to what we want to go is that you can ask yourself, if I have a set of indifferent options and I have a model AD, is this model indifferent with respect to this set? Yeah, in other words, is this model invariant under these indifferences? And that will be the case if and only if A is A plus I, and D is D plus I. Right, so this is what we call indifference of a model, in the sense that something is acceptable if and only if I add something that is indifferent, it's still going to be acceptable. Right. So that is what we call indifference of a model. Now you will remember that we associated lower and upper provisions with such models, and we associated precise provisions with this model. A model is going to be indifferent under these indifferences, if and only if the probabilities that correspond to that are going to be indifferent under these I's as well, right? So this very simple definition returns to the original definition of indifference when you go to probabilities. So this is generalization. Okay, now we get to symmetry. So suppose I have a set of options, right? U is my set of options. And now I have a collection of transformations, T. So this is a collection of transformations that go from U to U. So they turn options into options, measurements into measurements, gambles into gambles, right? And this T is a monoid. So I'm going to assume that it is closed under composition, that it has a unit transformation. So it is a model for a set of symmetries.
Oh, okay. You can make one parameter groups.
You could do whatever you want. You can have many parameter groups. So you could have all the translations if you want, or the gambles, or the rotations, or whatever you want to do, or the permutations of gambles. So this is this group of symmetries that you have. Then the question is, how do I express symmetry? How do I express that my model captures the fact that I believe that there is symmetry in the whole idea? How can I do that? Well, the idea is very simple. What I'm going to do is I need to construct from this a set of indifferent options, right? That is what I would like to do. So the very simple idea is, okay, if I have an option U, and if I have an option U and two symmetries, two transformations, then basically, since I don't distinguish between U and its transformation, or between U and the other transformation, I want not to distinguish between TU and SU either. These are also, for me, exactly the same thing, right?
So this is where I think I'm getting lost. So suppose that the U is
Function.
right. Okay, so the U has to be a function. So it's for example the fact that I'm gonna get $1 million if it's tail, or I'm gonna lose $1 million if it's head.
So suppose your function, you have some function on the space like you drew yesterday, and then this t could be the square, and the other one could be the square root, for instance. And then you say, if I think that taking the square of a function is something that doesn't matter, and then if I have a function, I should.
What does it mean that it doesn't matter? I guess
To you that you are convinced. Take permutation. I have that a permutation, that permuting the elements of it doesn't matter. Suppose that I do a sequence of experiments, right? Yeah, and I repeat the experiments, and my assumption is, okay, the order of the experiments is not going to matter for my inferences. I make an exchangeability assumption. Right, so
right, but that's the thing that I understand. If I switch heads from tails, it's gonna matter to me because I'm gonna bet.
yeah, no, but I'm just looking at for this example. Well, you could do that, but I'm going to make a more complicated example. I repeat flipping a coin.
Okay.
And then I look at the entire sequence of coins.
Yes.
And my idea is, okay, the order in which I observe these flips is not gonna matter. That is like a permutation symmetry that I could impose on the functions on all the sequences.
Oh, yeah, so the function of the sequence.
On all the
yes.
sequences. And that will, and so what I'm doing there is, if I have a gamble on these sequences, whether I permute it by one permutation or by another permutation, it should not matter. I should be indifferent between these things.
Now, I was thinking of the permutation of the elements.
No, but you could do that too. If you think that there is symmetry between heads and tails, if you feel that your coin is symmetrical,
No,
that should be the same. Then you also will have this symmetry between heads and tails, right? Then you'd say that the difference between a gamble where I permute them, heads and tails, and the gamble where I don't permute them shouldn't matter. I should also be indifferent between them.
Am I thinking about that as like, instead of calling it heads and tails, I could call it 0 and 1.
Sure.
That doesn't matter.
Doesn't matter.
Because I would still like make the same bet like if I don't know, for
Right,
some reason like tails more,
So-
I would like 1.
Yeah, but depending on this, I get completely two different scenarios. So if I say that I don't care about heads and tails, I'm gonna say that there is a 50% probability of getting tails. I'm fixing the probability.
Yeah.
If I say that it doesn't matter how I, the order in which I make the bet, then the assumption is
It's less restrictive.
well, it's just the independence of the statistical independence.
Yeah, conditional independence.
Right.
Yeah, but the idea is the same. You restrict, this is the point that I'm going to get to later on. What you do is you restrict the possibilities by imposing that type of symmetry. And in the case of heads and tails, the restriction is such that there's only one probability left over, because that's a very trivial assumption. But in more general cases, there will be restrictions, but they will leave you with some leg room.
All right, let's continue.
Right. So now what I have is that if I have an option, the difference between the two, it won't matter. So this belongs to my
difference
set of indifferent options. Now I can do that. I can do that for all the. So I'm going to do this here. I can do that for all t, s, and u. Right? And then because I need a linear space, I can take the linear span of that. Right? And this set, so the span of all the differences between t, s, and tu and su for all t, s, and u in the option space, this I will call the set of indifferences associated with this monoid. Right? So now all I have to do is, if I have check whether my model is symmetric, just means that m should be equal to m plus I, or in other words, this, but now for this monoid. Right? Okay, that's one thing. So now I have what we call a symmetrical model. Right? So for instance, if I take a precise model which corresponds to a probability, and this I is the set of all permutations, this model will be permutable. Or in other words, it will be an exchangeable model. That is what you can do. And now we have, then this is what I said before, a very simple idea, because A is a convex cone and D is a convex cone. And I know that A is equal to A plus I because of the symmetry. I know that my model is symmetrical, or IT. And my D is equal to D plus IT. This means that if I go to the quotient space, because I have a linear space, if I now go from U to the quotient space, I will be able to, I will have, so let me call that quotient operator Q. Then I know that I can work with Q of A and Q of D, because all the information, because of this equality, all the information will be in these images in the quotient space, right? And this is what you call, very simply, this is a representation. So because you now have a lower dimensional space, the quotient space, where all the information about your model is present, right? And this is how you use symmetry to reduce the complexity of a model. This is in essence what you do here. This is De Finetti's representation theorem for exchangeability. It's a very simple idea. You just use the quotient space of the symmetries to go to. So that is what I wanted to say. So any symmetry that you might have, once you have a probability model, you can use that symmetry to simplify the model. And this is why I said yesterday that if you, for instance, look at the indifference that is associated with not being able to tell whether the difference is zero, not being, because you can do it in polynomial time, that will give you a set of symmetries, and that you can use to simplify your model and hopefully, I'm not sure, but hopefully come to similar results as what you were saying. So whenever there is something that is indifference, you can simplify your model. And that's the only role that indifference has. You just collapse it to the quotient space and simplify the model. So whenever there are indifferences, whatever causes the indifferences, you get rid of them by collapsing.
Yeah, another thing that I don't understand is that the type of symmetries that we have in physics, I don't know that there are indifferences. Because if I translate it, I can measure that I translated. It's not that I'm indifferent.
Okay. Well, this I think is research that I think we both have been doing. They started this, but for instance, if you take the indifferences that are associated with permutations of particles, then you get exchangeability, so the quantum exchangeability theorem. You can do it even stronger. You can use boson symmetry, and then you get.
Those I agree that those are indifferences, because I cannot be able to say that, and the gauges are also this.
But you think you mean like time?
Right, time symmetries and so on. I can tell that I moved.
You can what? Sorry.
I can tell the time went on. So if I met the back to now or
yeah, but your system might have been the same, right? Or the beliefs about your system might have been the same. This is always about beliefs, right? About what you think about the system.
Maybe we can make a simpler example to understand like what we are different about. Let's say like a loaded dice.
What?
Loaded dice, like it's there. I know it's loaded.
Yeah.
Then I'm not indifferent about permutations, right?
Yeah.
So I would not pick that in mind. Okay. Does that help, Gabriel?
Again, it's a different type of symmetry, right? So the fact that I have a physical system that does a preparation, and that preparation has a symmetry, and therefore I'm indifferent to which particular preparation was done. That's one thing. But the type of symmetry that you use in physics, where you have yes, you have generators and all that. Those are not symmetry of your state of knowledge. They're symmetries of the space itself. And
Equations don't depend on
the equation
on your coordinate system for X
or the state
where you
space
actually
itself,
are.
because I can make the transformation and I still go inside the space, right?
Yeah.
On the other hand, I see what you mean. They're not the same thing, but they might induce symmetry on your beliefs, right? If I know that there's actually a law of physics that says that this is indifferent, then this has consequences for your beliefs if you want these beliefs to reflect what is going on in nature.
Right, so the thing that I was trying to understand, which I mischaracterized in my head, but maybe it's useful to mixerize things because then you find the real thing. So if I'm studying a system, right? And I say that this system is an equilibria of this set of processes, right? Then it means that each state is a symmetry of one of those processes. And therefore, the whole set of states is going to be a symmetry of the whole group of transformation, meaning that if I start with one thing that it's a symmetry, I will end up with another thing that it's a symmetry. But it's not a belief about the system. It's like those symmetries are defining what the system can be. And
we would do it the same quotient essentially, right? I think what to make sense of like
Right,
the difference using it would be like let's pick change of basis. That's a symmetry. It doesn't matter in which basis I express like a vector. So if you start with the actual sequences of components, I don't care which basis I use for that, right? Then my symmetry, my indifferences would be you could use that basis and then it would look like that sequence. Or I would pick that basis and have that sequence. I don't care about which
okay, so
basis.
we're
Then
using
you
the
reduce
trick
it.
of using passive transformations. We're not changing anything, we're just changing the labeling, right? So I will have because I have a symmetry because I have space and I can make translation, I can change the way that I label my points in space.
Yes.
So at that point, it's not that I'm now this is the delicate thing. The bets are gonna change, right? I care about what bet I'm gonna use. I don't care how it's represented.
Yes. So the initial space you would start with would be the specific representations of the bets, which there are many. And then you would be indifferent about which representation you use. Then you would take that quotient and then you would get just the actual bet,
Yes.
like independent of the representation. And then I don't add any more indifferences because now they're really different bets, right?
Yeah.
Does that make sense?
Yeah.
Okay, so yeah, I think we just usually skip that step or like we have already done it.
You've already done the
Yeah.
representation.
Yes,
Because
I
you
think
say
you're
that
right.
it doesn't really matter. Yeah.
We already think about the abstract vector and not of its components.
Right.
That's just saying the same thing.
Yeah, people who use, let's say if you use quantum exchangeability, you will start with the representation in terms of the
You
symmetrical
have
thing.
symmetrized or
Okay,
anti-symmetrized.
let's put it like this. We start with all the bets that could be made by all the observers with their own
Specific
framing and so on. And then I'm saying, oh, I'm indifferent between this particular bet of this particular guy and this other particular guy of this particular guy, and then I put them together.
And symmetry on the possibility space that can always be there. It's not going to affect this. This is something you have it. I don't know if you are on a ball or.
Okay, so then, but then, okay, so what would be the construction then? Like how, like what are the inputs, what are the outputs, and why should I care? I guess that's the.
But because basically by duality, what you get that you are going to have symmetry with respect to your element of the mixed space. So this is what is the duality, no? So like for example, permutation, if you have a probability, permutate the label will be the same. And
Your density operators will be symmetrical under permutations of the, for instance.
Yeah.
It would be like you start with a list and you go to a set, kind of.
Yeah, this is the part I don't understand what I'm starting with.
So in physics, you would start with like something in a very specific coordinate system. Like in everything in all possible coordinate systems. It's extremely overbuilt and nonsense. And then you would just throw that all out and you only take like the abstract independent of the specific coordinate system. Does that make sense?
Yeah, that's what I'm saying. So at that
starting-
point, there is no chance that I'm gonna do the procedure of pushing out the things, because it will be so overwhelming to even think of the space of all the possible things.
Yeah,
that-
but we just don't even do that. We already know this is like nonsense. That's the
But somebody
starting
at some
point.
point has done it. Right? I mean, somebody at some point must have made the argument that says that, okay, I ought to be using this, but I can use this because of the symmetry.
Okay, this is a good point.
Yeah.
Because somebody must have realized that, oh, the thing that I call X, you call Y, and they're the same thing.
Yeah.
Okay, so, but then it would be just a sort of conceptual abstract thing. It was not that something that I can actually then use to do something.
So I think this is important for foundations, not so much for calculate, because you will, once you realize this, you
Yeah,
will start,
okay,
you will
okay.
start in the right.
Yes, we agree on that, yes.
Yeah.
Yes, conceptually, we agree, like it's sort of making explicit things that we are implicitly doing.
Yeah. Yeah.
Yes, fine.
So, yeah, that's about it. That's what. Not a lot. It's, I mean, to explain this, it's quite easy. To write it down, it takes a bit more, takes a bit more effort.
Again, do you want to talk about also the permutation lab?
Oh, yeah, yes.
Ah, that one. Yeah, that one. Okay, okay. All right. Can I go to another page?
You just move it with your, no, up, go up.
Huh?
And at some point, we,
Ah,
there you go. Create a page.
it gets the message. Yes, so that was the idea where we said, okay, let's start with a set of acceptable options. And now the idea is I'm going to take, well, let's look at classical physics. I'm going to take a transformation of the possibility space, some transformation of the possibility space. So a map from X to X. And my options are what I call the gambles. So the functions f from the possibility space to the real numbers. Right, so I'm doing an experiment where I don't know the outcome, which is an element of this curly X. And then I take a gamble on the outcome, and that is a function that takes some outcome to a real number. Right, and this is a random, an uncertain reward. And the question is, will I accept these rewards or not? So if I have a set of, and the idea is now that my A and my D, if you want, that these represent complete ignorance. Right. So I had already proved that the non-negative gambles should be in A, and the strictly negative gambles, so the strictly positive gambles should be in D. This is something that I had already proved. You will remember, this is the argument of avoiding, well, it's something, so if something cannot give you a negative outcome, you must accept it. And if something must give you a negative outcome, then you must reject it. And put the minus in front, and you have the two things. So we have these lower bounds already on A and D, but what is important is to bound them from above. Right? Because we want to have more specification of what it means to know nothing in this context and in this language. And so in order to express what it means to know nothing, I need to impose bounds on A and D from above to become more precise, more specific about this A and D. And so one idea that you could use is you could use the idea that your beliefs in that case, so your sets A and D, which represent what you believe, are invariant under transformations of the possibility space of X. in that case. So whatever you do with the possibility space should never affect your beliefs. That is a very popular idea when you want to represent complete ignorance. You shouldn't, it shouldn't be affected. It doesn't work for probabilities, right? We know that it doesn't work for probabilities because probabilities, in my view, can never represent complete ignorance because they are
Right, exactly.
yeah, and so that's why it doesn't work. But it might work for a background. It might work for an imprecise probability.
Right. So this is where I thought that the transformation, the symmetries were on that.
On the probabilities.
No, not on the probability, but on the not the indifference, but what you just said.
Oh yeah, the accept and the desirability models.
Right.
The
The fact
vacuous-
the fact of what you don't know.
What you don't know. Yeah, the vacuous.
So I am symmetric, not the indifference, but on my lack of knowledge on the symmetry.
Yes, and so this A and D, yeah, but this, so it's not about symmetry anymore, it's about accept and desirability, and
Okay.
symmetry is derivative, right? If there will be symmetry, I will see what happens, right? But, so the idea is now, so assume that I got, that you tell me that or in the state of complete ignorance that you accept the gamble.
Yeah.
Then you must also accept, if this is true, if complete ignorance represents this symmetry, this invariance under transformations of the space, it must also be true that you accept the transformed gamble. How do I clean this thing? Is there a
Oh, there is a
I
there
see.
is a button on the
I
back
see,
itself.
yeah. So you must also accept this one. And what is this? TTF? TTF is a transformation that works on F by composing F with the small transformation T. So the idea is that TTF of a random variable X is just F of T of X.
Mhm.
Right? So I take the gamble not on X, but on the transformed X random variable. Right? And the idea is that if I accept a gamble, so the symmetry argument here is that if I accept a gamble on A, then I must also accept the transformed gamble, any transformation. Right? And so this
Can I ask a quick question? We know that this complete ignorance doesn't work for probabilities. Why do we think that it would work for this imprecise probabilities? What is in imprecise probability that allows this to work?
That is exactly what allows imprecise probabilities to work, is that that there is a background that does this, almost a single background that does this. And that is because precise probabilities are very, very strong information states.
Right.
Because they give you a yes, no answer to every question that you want. It's an oracle, right? If you have a probability via expected utility, you get a yes, no answer to any question that you fire at it. So it is a very complete information state. It is in terms of information content, they are maximal, right? And imprecise probabilities have a much lower information content. And so the hope is that for a much lower information content, you would be able to find models that are invariant under all these transformations. And I'm going to deduce one right now that does that. And it's called the vacuous model.
So in a sense, could you say that the imprecise probabilities don't pick up all the structure that you have in the symmetries in some sense? That is.
Yes, well, they pick up the certain imprecise probability models, because there's a whole range of them. Like let's make the analogy with logic, right? Just so in logic, so you have an axiom system, right? You have generation rules, and then the idea is I'm going to add a proposition, and what this will do is my axiom system will produce other propositions that are also true. So there's a conservative inference mechanism, so I can get then, and then if I add another proposition, I will again have all the consequences of that proposition, right? But there is, in logic, there is this minimal information state, namely my basic axioms, And then nothing else is true. That is my minimal information state. And if I'm going to add statements, I'm going to get a larger and larger set of propositions that are true until at some point I reach a complete theory. A complete theory is a theory where I have a set of propositions that are true, but if I add any other proposition, I get contradiction. So that's a maximal or complete theory. Well, the analogy with probability theory is that in probability theory, you have the same conservative inference argument. You can start from the minimal state of information, which is what is the vacuous model. You can add probability statements in the sense that I would accept a gamble like this. This is a gamble that I think is acceptable. And you keep doing this until at some point you can no longer add any statement without getting to contradiction. And those things for which you cannot add anything that is contradiction, those are the precise probabilities. Those are the probabilities. So they contain maximal information. Right? So in essence, geometrically speaking, if you have a two-dimensional plane, a convex cone is typically an imprecise probability model. If you get to a semi-plane, so your convex cone can go like this. I don't know if you can see me, but yeah. So suppose you have a convex cone like this. This is the smallest convex cone because it must include all the positive ones, right? So these are the positive ones, right? I'm going to increase it and increase it and increase it. I'm going to add statements, gambles that I find acceptable, until at some point I reach a semi-plane, right? This is a precise probability model because it's everything is acceptable that has non-negative expectation, right? This is a precise probability model. If I go further, if I add more, then my cone becomes the entire space, right? Because of additivity, right? It must be a cone, and it is this, so it will be the entire space. If I have the entire space, I will also include the negative gambles, which I can't do. So there are maximal convex cones that exclude the negative gambles, and those are the probabilities. So that is the analogy between logic and imprecise probability, is that what imprecise probability does is just it takes probability, but it adds the conservative inference mechanism that is behind logic in there, so that you can have more informed states of probability, which we call imprecise. And the precise ones are the fully informed states of probability. That is the idea. So what I'm trying to do here is find the smallest probability model, right? The one. So that is why I want upper bounds on this, right? So this is why. So small means as small as possible. As the A must be as small as possible, and D must be as small as possible. So I'm going to impose bounds on that, and the bound that I want to impose on that is going to be the symmetry bound. Okay, and now I'm going to go on. So this is my requirement for A, and I will have a similar.
I want to stop you one more time because I think I didn't understand anything before. So when you say that a gamble is indifferent.
But this is not. Let's not say it's. This is not about indifference. This is not about.
Okay, it's completely different. Okay, well,
Okay.
I'm still confused. But...
Yeah. So this is just the argument. Is there a smallest set? And what are the arguments for finding it? What is the background? How do you find the background? Because we know from my talk yesterday that the background is very important, because it determines what the probabilities, what the precise probabilities are in classical and in quantum mechanics.
Yes.
So I'm now going to do this argument. So the question is, this guy, what does it give? Right? So let's take a look. Let me take as I will call it Tx. So Tx, what does Tx do? I'm going to take a very special transformation. I'm going to take Tx that maps everything to the set X. So I'm just going to, and this is the lumping. I'm going to all elements are going to be mapped to the set X. So this means that Tx of f is going to be f of x, right? So it's going to be a gamble that takes a constant value in x, right? You agree? So I know that Tx of y is equal to x for all y, right? So f of Tx of y is going to be fx for all y. So tx of f in y is going to be f of x for all y. Okay? You agree? So I have a transformation.
Symmetry?
What?
Are we saying that this is a symmetry?
I'm saying it's a transformation of
Yes.
the space.
Yeah.
And my idea was I'm going to impose indifference or symmetry under all the transformations in the space.
Is it kind of saying everything is equivalent to x?
Yeah, well, I'm just saying, yeah, everything is x.
Okay.
So this is a very special transformation, of course, but that's the one that I need, right? In this case. And then, of course, now what we have is that if f is in A, then the constant gamble f of x should also be in A. But this is a real number, a constant real number, right? It's acceptable if it's non-negative, and I have to reject it because of this here. If it's a real number, and then it's going to be acceptable if it's positive, because then it's going to be in here. And if it's a negative, it's going to be in here, right? So since I must accept this, this means that f of x, so the first argument tells me that f of x must be greater than 0. Right? So what I have is that if any gamble that is in A must be and not have a non-negative value in x. And this, since x is arbitrary, it must have a non-negative value everywhere. Right? I can do this for any x. And so I know that if f is in A, then for all x, f of x must be greater than 0. So this tells me that A is a subset of g greater than 0. But I also already have that g greater than 0 is a subset of A. So I have completely identified A by this argument. Right? There's only one invariant set of totally invariant under these transformations.
For every x, I use the tx as a
Yeah.
transformation.
So, but that is, so what this tells you is that the lumping argument is crucial in this thing. And the question that I'm not sure of is, can you do the same by restricting yourself to the permutations? So would that be enough to get to the same? And that was a central question so it's easy if you look at the lumping functions, and then the argument is trivial. The question is a much deeper and I think that's related to what you were saying in your argument, right? That certain invariance is characterized by the polar invariant or the self-dual.
Yeah, homogeneous. So you want the transformation to preserve the positive cone.
Yeah.
And then I think for a specific positive cone, yeah, and you may need the permutation should be enough.
Should be enough. Yeah.
Yeah.
So it's probably, and that would, for me, would be more convincing, because I'm not very convinced by this lumping argument. I would be much more convinced if it were the permutations, because those are the real physical things.
Yeah. Right. So the thing that I'm confused about all of this. So when I have the background, right, there are gonna be some things that I don't know, right? It's basically all the things that I don't know.
It's those things that I accept if I don't know what if I'm in a state of ignorance. It's the gambles that I will accept
Correct.
when I know nothing.
So in that case, right, if I take so I cannot put it like this because I'm trying to understand how it maps to the model. So it's the gambles that I accept when I know nothing. So the basically then A is minimal under the conditions that I can assume, because in any other models my set A is going to become bigger.
Yeah.
Okay. So okay. So this in the context of imprecise probability is going to become a set of a probability distribution, correct?
Later on, I can transform this cone using the argument that you explained yesterday, that the lessons clear. There is a dual cone.
Right. So I can think of this as some type of sets of probability somewhere else.
Yeah. Yeah.
So there are gonna be within the set of probabilities, right? I can make transformations and I will end up inside that set. And that's gonna be a group of transformation that I can make on that space. And that will generate a group of transformation on your A's. And since you're closed in the group of the probability, you're also going to be closed on A.
Yeah. So your set of probabilities will be closed under all those transformations, not the probabilities themselves. They will not be invariant under the transformations. It's the set of the probabilities that is going to be closed under the
That's
transformations.
exactly what I was trying to get before. Like
Okay.
those are the type of symmetries that I have in physics.
Yeah.
That if I have my
Yeah, but that is a weak symmetry. That is because it's the set of probabilities that is closed under transformation.
correct.
Whereas the strong symmetry that is related to exchangeability is that it is the probabilities themselves that are invariant under the transformation. So an exchangeable probability in the sense of the Finetti is itself invariant under the permutations. So there's a crucial difference between a set of probabilities that is invariant, because if you take a probability and you transform it, you still end up in the same set.
Yes.
And you have a set of probabilities that are themselves invariant, because each element that you take is mapped to itself.
Yeah, correct. I want the first kind.
The first kind is the weak, what we call the weak kind of invariance.
Okay, because those are gonna be, so thinking about it like this. You don't know your probability space. You know that one probability is there, and then you have a group, and you know that you can take that probability and with a group move it everywhere, and you reach all the space, right? So this is again the first type of symmetry that you can use to generate your whole space.
Like for instance, the unitary transformation.
Exactly, right?
Where to bound that code.
Right. So at that point, those are the things that then I want to start thinking about to characterize this. Okay.
Yeah.
Okay, so these have nothing to do with the one that you discussed before.
The other symmetry is a much more reductive symmetry. That is the one that gives you strong results.
Yeah.
Okay.
And then that is easy to think. Think about the density metrics.
Yeah.
And you want the density metric to be like boson symmetric. But if you want the symmetry, all your density metrics might have that symmetry.
Yeah, but it could also be even more restrictive, like that I have, a unitary group that it's the rotation, and then I want to have the state of the density matrix that has that symmetry, and then I find the eigenstates of that operator, of the generator.
Yeah, but the point that all the elements of the mixed space, they have that symmetry.
Yeah. So you essentially get all the density operators that commute with the generator.
Okay. Yes.
Right?
Yes.
So that's not the symmetry that I can use to characterize the space. It's the other type of thing, that if I take all the possible transformation, then I'm closed
In the set.
Yeah, I think the case is the T of X there, no, that is on X, not on F somehow.
Yeah.
No.
So, and now what you were doing here is the transformation that takes everything and puts it in one point. And then you basically say, since I have to accept the positive gamble on that point, I need to take anything that is coming from there.
And that must only be non-negative.
Right. And so if you get permutations and you get anything that has that is accepting a gamble of 1 point, then you can permutate that one positive on the point, and you say, well, I have
It should be enough in a way. But I need a definite argument for that, because I haven't thought about this very long, but I would like to get a good argument to show that permutations are enough for this.
You need this to get to probabilities, is that the point?
Sorry?
do you need something like this, the lumping, which you want to get rid of, to arrive at probabilities in some sense? Where do you need this argument? Whatever you want to.
Well, because I need a background, right? So
Okay.
this is a way to get to the background, and it's the background that determines what the probabilities are, right? So in order to define what the probability is, you need to know what the background is.
So for me, this lumping sounds like, for each specific X, this sounds like someone knows that it's actually gonna be exactly
Yeah.
X. So they already know I can ignore everything, it will be exactly X. I don't need to look at anything else.
That's another argument.
And then it sounds like, what if
Yeah.
there is someone who magically knows which X it is?
Yeah.
And I don't want to be outsmarted by that guy. And I gotta make sure that for every single X, if someone knows, I can't be
Yeah.
outdid by that person.
That is another, I think it's a related argument. It's the argument from absolute certainty. Somebody knows it, and
Yeah.
and this must also be included. The background must also accommodate for somebody knowing everything.
Yes,
And that is it's a related argument that you could also use. Yeah.
maybe, yeah.
Yeah.
I think that.
I think it is something like that. For each F in the
Yeah.
in that guy there, in the G, we want that T of F is something like function of X that is always non-negative, so scaling, and this sort of, I don't know, this maybe needs to be projective, I don't know, something like that. So this is the kind of symmetry of basically it's something that preserves the positive cos. So I don't know what
Okay.
define this in general, but this is basically tell us that now we can scale.
Yeah.
And this is the transformation that allows us to map one point to another
To
point.
another point. And these will be the permutations then
There will be the permutation, there will be just a scalar. Like,
And so your point is, you're allowed to multiply.
Yeah, so
numbers
this is
and,
because I think this transformation does not need to be unitary, no, because it's the code we want to preserve. No? So this is the scaling can be different for each point, and this must be invertible because we want to go.
Yeah.
So I think this should.
This is a type of transformation that you could use to get to show that the permutations are enough.
Yeah, something like that, and and so I think this should be the most, not most general, but something quite general. So one needs to, I think this must be positive, and this we need to understand what this is.
And then once we have it for gambles, we need to do the same thing for measurements and show that all the unitary transformations are enough again to get to this.
Right, so what I'm trying to understand, so you're assuming that your Gamble's Fs are maps from some space to R, right?
From some space to R. Yeah, but this is in the case of classical probability. In the case of
Right, so, how would you generalize it if it's not discrete classical?
So the options in quantum mechanics are just the Hermitian operators. So they are measurements that I can take.
Okay, but you like whenever you're putting a symbol there, then you're making already an assumption of what space it is.
No. What do you mean? There, I'm looking at the special case of classical probability. So the options in my option space are maps from X to R.
Right, so you fixed an X, so you know what space it is.
Yes.
And when you're doing quantum mechanics, you're gonna fix a Hilbert space, so you know what the space is.
Yeah, I know what the space is. Yeah. And that's another of my questions. Can I get rid of all that underlying?
That's what I'd like to do. I
Yeah,
want you to be able to not know what space it is, fix the symmetries, and then you find the space.
Yeah, but we could do something a bit even more, like say, in general, that is, we can fix R to N. So we take the real part, the imaginary part, and then impose the symmetry to get the emission. We could do that, you know. That is like, you know, it would be probably more general, not but because we know the symmetries.
Well, this is what I'd like to do. Not have the X, have the ensemble space, and those Fs be linear functionals of the ensemble space. And then we put symmetries on the ensemble space, and then you know what the ensemble space is based on the symmetry.
Yeah, and that would give you a background, and it would give you a set of probabilities that you can work with. Those
But
would be,
you should tell me what the ensemble space is at that point.
yeah. Well, but
Right, because so I put the ensemble space. I don't know what the ensemble space is,
yeah,
right? And I just know that, well, if I'm putting the ensemble space there, I know that that there exists an ensemble space with those things,
but
that for every
yeah.
point, and then I have some set of gambles on the ensemble space that I still don't know what it is because I just know that it satisfies these higher axioms. And then I have the space of gambles, which is just a set of linear functional. And again, you still don't know what they are.
Yeah.
And then you impose some symmetries, and then basically that constrains what the gambles are. And that endpoint should constrain what the space is.
Just to add something else, because you say you can have a version of this where you don't have an underlying space, right? So this is work that was done in the 70s by Peter Williams. So you could have abstract things that are called variables, right? They're not functions from a space to the real numbers. They're just variables that live in some linear space. And the only thing that you have to define on that is, again, is what if you see is an infimum operator, some notion of infimum on that space, and that is enough to give you a theory. And this is actually also what we're doing here, because what I'm doing here is I'm imposing a norm, and that norm gives me an infimum operator because it gives me, or a vacuous thing, and that gives me an infimum operator, and that is enough. So the idea is if you have the symmetries and you allow the symmetries to give you to allow you to define an infimum operator, namely the smallest infimum operator that is invariant under the symmetries in that respect, then you will have a theory of imprecise probabilities without any underlying space, just abstract things that take values but not functions from anything to anything. Right. So that is what we call spaceless probability. So maybe that could be.
Yeah, I'm trying to understand what is the right.
Yeah, I think so. I mean, I got inspiration from what you said by listening to what you were saying and infer from that.
But the other things, I'm not sure that if the gamble should be in the mixed space, no, because you will not recover the duality that you have in probability, no. So I think so there is this idea of I think you might see now what you call it the capital F. Okay, the capital F is some sort of the embedding of the mixed space. So the gamble is the dual of that in the vector space. Okay, so I think because otherwise you lose this analogy with the background. I think.
Yeah. Okay, so that basically have to be the function from the states and not the ensemble.
Yeah, exactly. That is something that to me it's good because it's about you're putting the gamble on the things that you.
Yeah, but I don't know what they are. I want to find what they are based on the symmetries.
Yeah. Yeah. So yes,
and then I have these one parameter groups. So since I can make these moves that I want to, that's where I get the space.
Yeah, then I think you have you need to start with some symbols and then impose symmetries and work with I guess it should be equivalent what you are doing at the moment somehow.
So you want to go from your ensembles but get the dual of the.
Yeah, exactly. So in an abstract way,
Yeah, but and could it have meaning? Could it mean something?
Because I want to be able to also make the bet that I have on the ensemble, right? I'm betting that it's a fair coin, right? So for me, the fact that the process is a fair coin, it's a possible preparation.
No, then it's for sure you can do it, but I think you.
But then I have a probability on the ensemble, which is not what I want.
Yeah, that's I think is not what you want exactly.
You want to go to the dual problem.
Yeah, you want to go to the dual and understand basically how you can do an abstract dual that is something equivalent to the mixed space where you don't want to define the underlying X.
And then you can do everything that we do here, but on that dual space, and it will
And as you define the operation in the mixed space, I think you needed to define a sum in the other space that and a scalar multiplication, and then let's see what it is.
idea.
Yeah.
Okay, so let me understand. So I have the ensemble spaces, then I get the dual, but then the dual, I think it not as a function from the ensemble space, but I think it as a function on whatever the points are gonna be. Then I put symmetries on those dual, and you're saying, then you're gonna find the points.
Yeah.
And then you're gonna be able to say that the ensembles are actually some type of distribution,
over the points.
precise distribution of the
Yeah,
point.
you find X, whatever it is.
And that's the way that I found the X that I don't know how to do yet.
So you start assuming there are some X, there is some space. And the only thing you tell me about that space is what symmetries are on it, right?
Yeah.
But you need to assume there's some space, otherwise it doesn't make sense to talk about symmetries.
No, because I'm talking on the symmetries on the Fs, on the gamble, right?
Well, here there are induced by maps on that X.
Right, I will just talk about them as symmetries on, because now what's gonna, so imagine that I
Yeah.
have my Poisson structure,
specify.
right? The Poisson structure tells me the evolution of the statistical variable on those, right? I'm translating, I don't know what the ensemble space are doing, but I know what the position is doing. I know what the position square might be doing and stuff like that.
Yeah, you will specify it in terms of what it does to your F.
To
And it
find
will then
functions.
turn out to be some kind of map on the underlying space, but you will find the space and then.
Yeah.
Yes, yeah. Okay, but there is some space.
But in that case, X will X be the position and moment or not?
It may or may not, because if I'm in quantum mechanics, then I should be able to talk about the transformation generated just based on my Lie algebra, right? So at that point, I don't even know that there is a unitary transformation in some sense. I have the Lie algebra, and I don't know what. And again, I will have to know the complete Lie algebra at that point, because I can't just know X and P, because I need to know what the products are and all that. But in principle, then because I have the two different Lie algebras, I would be able to say, oh, this is the classical one, this is the quantum one, and then the X's are going to be different.
Yeah, it's about what we were trying to do with this polynomial, because instead of abstract, variables, whatever it is, it's what polynomial are in a general way, to be able to define this gamble in an abstract way.
Yeah.
And the fact, so with that X in the polynomial that we have, they don't have any meaning in whatever the variable are. I mean, it doesn't matter, no? And it's somehow it's the same thing. You want some variables, and then you want to define the symmetries on these variables.
Yeah. It's just that in my case, those variables are the generators of unitary transformations, and I know what they are. Yes, it's gonna take months to digest all this.
But this is how you, even in field theory, define, like especially quantum field theory, define like the spaces, right? You're like, it has to be a representation of this group. I know what it means to shift my particle in space. So I have to have some space in which I can act. I don't know what the space it is. And I use the smallest one, I have an irreducible representation of that group and so on. And it should be all that stuff.
Yeah, exactly. I want to take that stuff and put it in the context of probability, so that I get ensemble spaces on top of it. Because then the problem is, if that works and I can then extend it, then I can find my probability space for fields, because I know that all these symmetries are there, and then I don't care of anything else. That should be the minimal thing, and maybe the minimal thing with turning the trunk gives me, the correct topology, the correct whatever things that I need to tame these spaces.
This would also make me feel much more comfortable about your approach, which was based on precise probability in it. in a way, because if you go to the dual, you don't need the precise probabilities anymore. You have much more freedom. And so my problem is always, why do these precise probabilities have this special status and special meaning? But they don't. In this case, they just become special representations of something that in principle has much more freedom. But you just use them as components for.
Yeah, and then in the ensemble space, as you said, like I don't really have probabilities.
Yeah.
It's I have mixing coefficient because I need to be able to use those mixtures. The fact that in classical mechanics I can represent things with probabilities, that's good and fine.
Yeah.
And at the end of the day, I want, as I said, sets of ensembles for me are more important than the ensembles themselves.
Yeah.
And so in a way, sets of ensembles are gonna be
Sets of probabilities.
No, the thing I'm curious is what we could the role of entropy here.
Yeah.
Because it's something that we don't use, and I don't know why.
I don't know why. Yeah, it's the first time you're talking about it made me realize that my hatred of the notion of entropy was maybe unfounded. Because it's been used in very horrible ways.
It is used in terrible.
Yeah. I mean, in probability theory, when you use entropy to select one probability from a set because it has the highest entropy, and that's somehow supposed to mean something, that is something that I find very scary.
So that's the thing also that I'm trying to understand in a better way, because it works in a lot of cases. So it means that there has to be some, statistical mechanics to do the, but I do not know if it works because like that's really the thing that you have, or because you have a class. So how do you do it in statistical mechanics? Typically, you have some bounds, right? You say this is the energy, this is this, and so on. So now you have a set of ensembles, a set of probabilities, and you're somehow picking one as the representative, right? And there is a sense that when you do that constraint, you can imagine that there is still a system, a macroscopic system that is doing something, right? And it's fluctuating in a way that does not change the macroscopic variable, right? And there is a sense that if you're not sensitive to those fluctuations, you kind of don't care which representative you get, right? And so my question is, when we're maximizing entropy, are we picking a representative that is convenient and somehow the one that maximizes entropy is the most convenient? Or there is actually a process that is injecting randomness with those constraints. And if you're injecting randomness with those constraints, you're going to get the maximal entropy, because every process that is injecting entropy, injecting a randomness, is getting entropy inside. And that's the part that I don't know which is which.
Nobody knows. Because that is a very deep, this is a deep philosophical question, right? Is there a process that injects randomness? It's like making assumptions about what nature does.
It's an assumption of whether you are completely isolated or you're not isolated. You are in equilibrium that you still.
So you're saying that there might be a mechanism from the environment that does this. Okay.
Also because I think what you could also do instead of doing the maximum entropy is to impose symmetries. Because think about the Gaussian case, where you have mean invariance, so your two constraints, you get a Gaussian, but you can also get the Gaussian by symmetry. So that you could also add instead of finding the maximum entropy distribution.
Yeah, sure. Like the picking of that might also be equivalent as imposing a symmetry, right? But that symmetry to me would be the equilibrium. Yeah, because it's if you're interacting with an environment in a way that you're you're getting at the equilibrium when you've maximized the entropy. So again, that's another thing that I want to be able to link is the idea of equilibrium with symmetries.
So I agree that when you work with physical systems, there might be reasons to do this, but when you're talking about knowledge?
That you have
Then I
one
think,
hundred percent.
yeah,
So
yeah, then I
for the
think,
knowledge,
why?
the only thing that I could think is, well, I don't care about these things. Oh, this is more convenient, and I will use that.
And it's precise. I can calculate with it. Yeah.
Exactly, right? I can do something with it. So, yeah, that I agree. No, the fact that the minimal state or maximal state of knowledge is that, no, that I completely agree. It's complete bull, yes.
Yeah, I think, the fact that you define the extremes, the orthogonal with the entropy, then maybe tells also something about the transform, because basically what those kind of transformation in somehow, I think they have to preserve the extremes. They have to map an extreme on an extreme.
Yeah.
And then maybe it's a way you could define extreme, I guess, through the entropy in a more abstract
Yeah,
way.
yeah. So if you have one of those transformations and you're kind of saying, oh, I'm indifferent, you have to say that they are conserving the entropy, because the non-conservation of the entropy, it's like contradicting the fact that, oh yeah, I can change this to that, and I didn't, you can't have a background that has symmetries that move entropy up and down.
Yeah.
That would make absolutely no sense.
Yeah, I think it's something that we always struggle to define, what we call the evaluation function, as they are the extreme. That it's somehow the things that evaluate the gambles, no?
Yeah.
And I think this is something maybe, there should be this somehow a sort of, you can use the entropy, or there must be some dual of the entropy.
You need something to do it, because it's as I said before, it's independent information. You can take the triangle, cut it.
Now, about that, I was also thinking, but could you do in that case try to use some sort of isomorphism with the original triangle to get back to the extreme, some sort of like
On the convex space, yes,
Okay.
not on the entropy.
Okay.
So the entropy, if you change, if you put them back, then things that weren't orthogonal, they become orthogonal. So you're in some sense decreasing the entropy of these things. And from the physics perspective, that's not an isomorphism, because you really changed the system.
No, but what I was thinking is it's like redefining the S on the streams, instead of being zero. Let's assume that in this restricted triangle is a constant that is not zero. Basically, rescale everything. So it is zero. Okay, do the computation there, and then maybe go back. Would you do this?
Yeah, but so for us, S is the variability of the preparation. It's a physical thing.
Okay, so you can, but you can.
Yeah, mathematically you can do whatever you want, but then when you make a prediction, it's not gonna match the physics.
No, I was thinking about if you could recover the orthogonality in that way.
And no, because the orthogonality is the fact that those two precisions are spitting out things that are different.
So these are given to you, so you cannot.
It's part of the physics, yeah. And I completely understand if you have a purely probabilistic model and you don't have this notion, then you really don't have it. So you're free to do whatever you want. Right? It's the same thing in thermodynamics, right? I have my states, the macro states, they have an entropy. I can just change the entropy however I want, because when I put them together and I make them interact, they're gonna be doing different things.
Yeah, but because the only thing is I was thinking, because you say that I don't know how to put the entropy on those strings. That is something that is not fixed by the definition of the entropy that you have.
Oh, because I'm missing an axiom. That's
exactly. So I was thinking that if you can simply, I don't know, move this and.
No, I can do it because I don't have enough constraints. It's not because I should be able to do it. I know that I should not be able to do it, but the axiom allows me to do it, and it's I don't have. That means that I don't have all the properties that I should need.
Yeah, I think it would be really interesting to see this in the dual way, because it's so what you can get to the other side.
The gambles,
yeah,
right.
On the gamble to see understand what the similar problem is.
Yes, and the problem that it's a nonlinear function, so I don't really like. I don't know how it transports from the dual.
Because you use define a sort of norm, or define that when you find that what you call it the MS.
Yeah, but the MS doesn't get all the entropy. Only get entropy differentials. In fact, the topology of the MS generated by the MS is not enough to make the entropy continuous.
Okay.
So if the entropy is continuous, MS must be continuous, but the other
then we're not
way is
on
not.
time.
So it's and the reason is because the thing is a difference between two things. And so you could have the two things going to infinity while the distance remain finite. And so the MS does not pick up that things are going to infinity.
Fascinating.
14 minutes into our scheduled lunch break. Before we lose Susanna and Marcel, that I assume won't be here after lunch, I thought maybe we could try to take a picture with the seven of us.
Okay, cool.
Yeah, I think I could make the extra, but I think we should stand under one of the panels, and I think
Hide your own. No.
I think we just say turn off our video, and then it'll hide us automatically.
Hide self view.
Oh, there we go.
So that they can still see us.
Yeah.
Because now we're gonna talk and the video is gonna see us. Who's taller? You're taller.
Oh, there's Ben. Oh, let me turn off the ceiling light.
This is better than using Photoshop, I would say.
A very long arm.
Well, it's not a very long arm. I can take it like this. Actually, you go here because then my arm can be here. Oh, right. Okay, everybody more there?
Over there. Almost.
Cheers.
Susanna is almost out. Yeah. Great.
Okay.
I can send you guys.
Okay, cool. Is that enough? Yes.
See everybody. Fun.
I can restart it.
All right, thank you. So, you can turn on our video.
Yes.
Thank you so much for your participation, Susanna and Marcel. I find it difficult to call into multi-hour Zoom remote meetings. You done well in the marathon.
Very brave.
Thank you very much for the invitation.
Thank you very much.
Too bad we couldn't be in person there, but it was very nice to participate, even if it's from a distance.
Yes, we appreciated your participation very much.
Yeah, I think we all learned a lot, so that was very useful to me at least.
It was nice to meet you. Also.
Okay, so we will, for those who will be joining, and we have a couple of participants on Zoom, if anybody who'll be joining or people in the live stream will come back at 2 p.m. US Eastern time, so an hour and 13 minutes. Okay, goodbye. Bye.
Bye.
Goodbye. Bye.
Okay, so stream is